This is a video about Rust, and it's not a video where I try to convince you to use Rust, because, let's be honest, you already clicked on the video. This is a video of 96 exercises from the Rustlings repo that I'm going to take you through from the perspective of somebody who uses not C, but JavaScript or Python or something more like that. So if you want to go from, I don't know any Rust, or I just know a little bit of Rust, to, yeah, I can write some simple programs. I know what the base types are, and I know how they work, and I've seen some programs, and I've worked through a couple of them myself. If that's where you're looking to get, and that's where you are right now, then this is the video for you. Of course, there probably is something in there for everybody, and there are a bunch of chapter markers in the description, so you can go find the places that you feel like you might not have a firm grasp of, and go learn a little bit more about it. So let's get started. To get started with Rustlings, you'll want to head over to the rustlang/rustlings GitHub repo. Scroll down to the Getting Started section, and if you've never installed Rust before, make sure that you go through the Getting Started to get Rust up and Rust itself installed. Now I'm on Mac OS, so I'm going to take this first curl command, which fetches an install.sh script and pipes it to bash. After pasting the command into your terminal, you'll see the script download as well as a number of checks run. The repo will check out a specific version. In this case, we're using tags 521. And notably, between major versions, Rustlings mostly adds exercises. So if you are on 523 or 53 whatever, or often even 6, this video is still applicable. After cloning the GitHub repo and checking out the right version, the script will install the Rustlings executable. If you've never installed a Rust program before or built a Rust program, this will be the first Rust program that you actually do build. And you can see that from downloading all of the crates from crates.io. And in this case, it's replaced an old install of the Rustlings CLI that I used to have. It says run Rustlings to get started, but if you run Rustlings now, it will also tell you that you need to cd into the Rustlings directory. It just cloned this repo, which is the rustlang rustlings repo, so make sure that you cd into that directory before running Rustlings. After running Rustlings, you'll get a short introduction. The intro paragraphs include a number of suggestions as well as some useful information. The central concept behind Rustlings is that it is a set of almost 100 or more exercises at this point, which you can then try to figure out on your own. Sometimes these will be small syntax errors, and other times these will be major logic errors, or entire function bodies that you need to write. It's recommended to run Rustlings in watch mode, which will track your progress as you complete each Rustlings exercise. However, be aware that if you complete an exercise, the Rustlings watch mode can move on to the next exercise without you quite realizing it, and you thus might be seeing errors for the next exercise. So make sure that if you see an error and you're confused by it, that it applies to the exercise that you're actually trying to work on right now. Rustlings says that if you're stuck on an exercise, there's a helpful hint you can view by typing Rustlings hint or hint in watch mode. Personally, I feel like the hints are pretty required for a lot of the exercises, because without them, you're not really sure what Rustlings wants you to do for a particular exercise. So I'll be showing you the hints as we go through these exercises together. Of course, Rustlings is an open source project, so if you have difficulty with it, or you want to make suggestions to the project or contributions, you can find that at this link on GitHub. It also says if you want to use Rust Analyzer with exercises, which provides features like auto-completion, run the command rustlings lsp. Now, I am so used to using Rust Analyzer when I work on Rust code that not having it feels like I'm being constrained into a software engineering interview. You know, the kinds of interviews that's like, here's a marker and a whiteboard, good luck. So I'll be running Rustlings LSP. After running Rustlings LSP, it determines a tool chain. A tool chain in this case is just the computer that you're running Rustlings on. You can see that I am on an M1 Mac with the Rust stable release. M1 because it's AArch64 Apple Darwin. It generates a Rust project.json, and it tells us that Rust Analyzer will now parse the exercises, and that we should restart the language server or our editor if we've opened it. You can see that the Rust project.json is a bunch of JSON. It's not required that you understand this. It just points to each of the files. And with that, I'll open VS Code. There's a number of files in the Rustlings repo, but the ones that we care about are all in the exercises folder. They aren't ordered inside of this folder. They're ordered by the Rustlings CLI. So when we run Rustlings watch, it will point us to the next one. So don't try to go through these in alphabetical order or anything. I'll run Rustlings watch to get started. Rustlings watch starts off showing you a progress bar. There are 94 exercises in the repo currently, And right now it's running exercises intro1.rs and tells us that the code is compiling. The output that you'll see with Rustlings Watch isn't the same output that you'll see if you try to compile these exercises on your own using Cargo or something like that. This is a specialized CLI, which will show us the information we need, but doesn't quite provide the same exact experience as doing a Cargo build or a Cargo run inside of your Rust project. We can see the output of our program here, saying hello and welcome to Rustlings in some ASCII art. This exercise is only responsible for making sure that everything compiles on your computer at all. So there are no problems in this program, but we can still open intro1.rs and take a look at all of the print lines that are printing out this information to the console. So you can see the output here from hello all the way down is given by a series of print lines that print one line at a time to the output. When we're done, we have to look for this comment that says I am not done and remove it. And that will move us on to the second exercise. And you'll see that the progress indicator moves to 2 of 94. And then we start to see compiler output. So compiling of exercises intro2, which is the next file that we need to open, failed. Please try again. Here's the output. Each exercise file has a comment at the top of the file that explains what we need to actually do inside of this file. That combined with the hint will tell us what we need to do to complete each exercise. In this case, intro2.rs says make the code print a greeting to the world. Of course, it doesn't tell us what it wants us to print. So if we type hint in Rustlings Watch, it says add an argument after the format string. So maybe it doesn't matter. So for me, I've done YouTube here, and we can see that that prints out hello YouTube on the left. Now let's go back for a second and read the error message. The error says one positional argument in format string, but no arguments were given, and then gives us line 8 and points us to this little curly brace thing. Print line with an exclamation point is kind of like console log in other languages. In Rust, this is referred to as a macro, but we'll go over macros later in the video. The first argument to print line is a template string or a formatter. In this case, we have a number of characters and then 2 curly braces and then another character. All of these regular characters will print out, but these curly braces are kind of like saying the first argument we pass into print line will get put into the string at this location. That's why adding the second argument places this value, whatever value we want to put in, at this location inside of these curly braces. So what the error message is saying is that there's a positional argument in format string, but no arguments were given. This display formatter right here is what this is called, is what indicates that we need a positional argument here. And that's what this error message is telling us. So if I put YouTube here, then we have successfully ran exercises intro2, the code is compiling, and the output is hello YouTube. Of course, when we're done, we remove the comment, I am not done, and we save and we can move on to the next one. The next exercise is variables 1. In this case, the only instruction we have in the comments is make me compile. And if we type hint, we can see that the declaration on line 8 is missing a keyword that is needed in Rust to create a new variable binding. So here we have a main function. The main function in Rust is the entry point. So if you run a Rust binary, what you are running is this main function when you start your program. Here we're trying to set the variable x to 5, and we're using the same printline macro that we saw in the intro with a positional argument x. In this case, the Rust error messages say cannot find value x in this scope, and it gives us a line number on number 8 and points us to x, so not found in this scope. And then again, we have another error on line 9 that says that x is also not found in this scope. Now we can ignore the second one because the first one is causing the second one. In Rust, to declare variables, you need to use let, whereas in other languages, this might be var or some other name. In Rust, variables are declared with let, and they're immutable by default. We'll get to what immutable means later. But now we've introduced x into our program and set the value to 5, and then we've used that number to print out x has the value 5 into our output on the left-hand side. Once again, when we're done, we can remove I am not done. And here we are in variables 2. Variables 2 doesn't even include the phrase make me compile, so we'll open up the hint here. The hint is saying to read the compiler message. So the compiler message is saying that Rust cannot infer the type that the variable binding x has with what is given here, and then gives us a number of questions. So let's go back to the exercise output. In this case, the Rust compiler is telling us that there are type annotations that are needed on line 7 at position 9, which is the x once again. The Rust compiler has helpfully suggested consider giving x an explicit type, and it's given us the syntax for defining that type as well, with this colon. So there are a number of things that can happen here. If we just set x to be some number, then we've filled x with a value, and our compiler will compile the program and give us our output. In this case, the main function sets x to 0 and then checks to see if x is 10. If it is 10, then we get x is 10 and printed to the console. If it's not 10, then we get x is not 10. Now we can choose to give a type annotation here if we want to. So if I do something like let x equals 0 as a U8, then our code still compiles and runs because x is supposed to be a U8. That's what this colon is. We're saying that the variable x is going to be a U8 and we're setting that equal to 0. Now a U8 is an unsigned 8-bit integer. The specific meaning behind what that number is doesn't really matter to us right now. But if we use a different type, like an F32, which is a float, so an integer doesn't have a decimal place, and a float does have a decimal place. So if we try to declare x as an F32, but we use a value that's an integer without a decimal place, then the Rust compiler will tell us that we have mismatched types. And it's very explicit. It says that the value that we're giving it was expected to be an F32, but we found an integer. And it gives us a little bit of help. We can use a float literal if we really want to make this be an F32, and we can do that in both places. So if we use decimals, this can be an F32, and our code will then compile again. Depending on what language you're coming from, there will be either vastly more number types than you're expecting, or exactly the number of number types that you're expecting. JavaScript, for example, only has one number type, so learning what the different number types are is going to take a little bit of effort, but they are useful to use in different places. For example, we said x was a U8 when we started out. A U8 can only contain the values from 0 to 255, which if you're coming from the front end or from a CSS background, you'll notice is exactly the number of values we need to represent red, green, or blue in a CSS declaration. But for now, we're done with this. So let's remove I am not done and move on to the next one. So here we've got variables 3, which is a main function, an x declaration, and then another print line, just like we had before in variables 2. The Rust compiler is telling us that used binding x isn't initialized, so we are not setting x to any value. We're just saying x is an i32, which is an integer. Again, that means it doesn't have a decimal point, and the Rust compiler helpfully tells us that the binding for x is declared here, but it's left uninitialized. That is, it doesn't have a value. And then we try to use it before it is actually initialized. So if we type hint, we get, oops, in this exercise, we have a variable binding that we've created on line 7 that we're trying to use on line 8, but we haven't given it a value. We can't print something out that isn't there, so try giving x a value. In my case, I'll give it the value 0, which will compile and run as expected. This is the same code we had in the last exercise, so it shouldn't be surprising that this code compiles. If it is surprising, go back to variables 2 and rewatch that exercise. Now we're done with variables 3, so remove the comment and save again. Variables 4 is another main function where we declare x to be 3, we print it out. We try to declare x to be 5, and then we print it out. Now we're not supposed to change line. Now it's important that we don't change line 9, as there's a comment here that says don't change it. The compiler error says cannot assign twice to a mutable variable x. We mentioned earlier in one of the other exercises that variables in Rust are immutable by default. And what this means is that you can't change them. So if you declare x to be 3 up here, you cannot redeclare x to be 5 down here. The Rust compiler, help text here, gives us exactly what we need to fix this program. Consider making this binding mutable, mute x. So while variables are immutable by default, we can include the mute keyword here to make x mutable, which means that we will be able to change it on line 9. So now what we've got is a mutable declaration for x, set to 3 originally, printed out, reset to 5, and then print it out again. And you can see that in the output on the left. Defaulting to immutable variables is one of the things I really enjoy about Rust, because it makes it very clear by default which variables in your program are being changed over time. We're done with variables 4 now, so remove the comment, save, and let's move on. In variables 5, we have some program that we need to get to compile. We're not allowed to change line 7, and we're not allowed to rename the number variable on line 9. So if we type hint for what Rustlings wants us to do, it says in variables 4, we already learned how to make an immutable variable mutable using a special keyword. That's the mute keyword that we worked on in the last exercise. Unfortunately, this doesn't help us much in this exercise because we want to assign a different typed value to an existing variable. So that's let number equals this string 3, and then later on we try to make number equal the number 3. Sometimes you may also like to reuse existing variable names just because you're converting values to different types, like in this exercise. And then they talk a little bit about shadowing. So the solution they want us to do here is to redeclare number as 3. If we add a let on line 9, like we have on line 7, we declare a new variable called number that is equal to the number 3. This is the concept of shadowing in Rust, where we can have one variable that is declared to be something, and then we can use that same name later on to declare a new variable with the same name. This can be useful in a number of situations, and it is something that many people like about Rust. But it can also be very confusing because all of these numbers are the same variable name. The number on line 9 shadows the number on line 7, so that anything past line 9 will refer to the variable declaration on line 9, and anything before line 9, like on line 8, will refer to the number defined on line 7. This is basically the same as this effect, where we have number defined on line 7 and used on 8, with num defined on line 9 and used on 10, except for the fact that we're taking the original number out of scope, so making it inaccessible to later lines in our program. So now that we're done, make sure you remove the comment, and let's move on. Here we've got a program that tries to define a constant called number that is set to the number 3, and then tries to use that number to print out to the console. Const is a very different keyword than let. And while it looks like they do very similar things, constant or const means that this is being defined at compile time and executed at compile time rather than being executed at runtime. So this number will always be 3. The hint text again includes a little bit of explanation. We know about variables immutability, but there is another important type of variable available, constants. Constants are always immutable, and they're declared with the keyword const rather than the keyword let. Constant types must also always be annotated. And of course, the Rust compiler is already telling us this up here. The error is missing type for const item, and the help text says provide a type for the constant, and it suggests a type i32. i32 works for us because we aren't doing anything particularly interesting with this, so we can save that. And we can see that the program does compile and print out the number 3 now. Now that we're done with variable 6, remove the comment and move on to the next one. Now we've made it to functions 1. In functions 1, we've got the main function defined as we've seen in all of the other exercises. And inside of the main function, we try to call a function called callMe. CallMe doesn't exist though, and the Rust compiler says, hey, I can't find a function called callMe in this scope. If we type a hint for this exercise, Rustlings is asking us to define this function. So to define functions in Rust, we have to use the fn keyword, followed by the name of the function, parentheses, and any arguments that it takes. In this case, it doesn't take any, followed by the body of the function with curly braces. So in this way, we've defined a function called callMe in very much the same way that the main function is defined. It doesn't do anything, but it exists. From here on out, I'm not going to remind you to remove the comment at the top of the exercise. So every time we switch to a new exercise, remember to remove that comment. Functions 2 includes a program that includes a main function and a function called callMe that accepts an argument 3, and a function definition called callMe that accepts an argument num that is missing its type annotation and prints out a set of numbers. The Rust compiler once again is telling us that at the function called me, it expected a type and it found an ending parenthesis, and that it expected a type right here between the colon and the parenthesis. Also of note is the fact that because we have this syntax error, there's an error below that that is caused by that syntax error. So the errors that you want to read that are probably the most important are the errors that are at the top of the error readout, because those errors can cause other issues down the line. And if we fix the first one, the second one will go away. And the hint for this exercise is that Rust requires all parts of a function signature to have type annotations, but callMe is missing the type annotation for number. In this case, I'll choose U8 as the type, but you can choose any number type you want. Because we're dealing with integers, you probably either want a U8 or a U16 or a U32, which is an unsigned integer, or you want an I8 or an I16 or an I32, which is a signed integer. Numbers in Rust are defined as the type of number and then the amount of space that we allocate to represent those numbers or to store those numbers. In this case, 8 is 8 bits, 16 is 16 bits, 32 is 32 bits, and so on. So an unsigned 8-bit integer would start at 0 because it doesn't include any negative numbers, and it includes enough space for 256 numbers, so we would go from 0 to 255. A signed 8-bit integer contains the same amount of space, so 8 bits worth of space, which can hold 256 numbers, but because it contains signed integers, which means negative and positive numbers, we use that space differently, and the lowest number an I8 can represent is negative 128. The highest number it can represent is 127, which is still 256 numbers, just in a different place on the number scale. This program also uses a for loop to print out the numbers, as well as a range. We haven't covered iterators, for loops, or ranges yet, so don't worry if you don't understand this. I'll cover it briefly here though. A range in Rust allows us to specify some number as the starting point and the ending point. So in this case, if we specify 3, this range is a range from 0 to 3, and we do that with these little 2 dots here. So this range represents the numbers 0, 1, 2. A range is also what we'll call an iterator, which allows us to use a for loop on that range. So if we use a for loop, this I will be each of the values from this range. So because we have a range from 0 to 3, non-inclusive, we will get the numbers 0 in I, and then 1 in I, and then 2 in I. Now you'll notice our output is 1, 2, 3, not 0, 1, 2, but that's because we're adding 1 to each of the numbers when they come in. So 0 plus 1 is 1, 1 plus 1 is 2, and 2 plus 1 is 3. Again, we cover iterators later, so don't worry if that doesn't make a ton of sense to you. Let's move on to functions 3. Functions 3 has the same main function with a usage of call me that doesn't have a number passed into it. Our function definition for call me accepts a number that is a U32, so it's a fairly potentially large unsigned integer. And then the code here is the same code we covered in functions 2 that iterates over and prints out these numbers. So what it looks like is that we're going to have to add a number to call me. Note that the Rust compiler is telling us that this function takes 1 argument, but 0 arguments were supplied and points directly to call me. Let's check the hint, and the hint confirms that this time the function declaration is okay, but there's something wrong with the place we're calling the function. So I'll use 0 again inside of call me and save, and we get compiling code. Of course, 0 doesn't give us interesting output, so I'll use 5 here so that we actually do get more in the range. And let's move on to functions 4. Functions 4 has more of an explanation for the exercise than we've had previously. It says the store is having a sale where if the price is an even number, you get 10 Rust bucks off. But if it's an odd number, it's 3 Rust bucks off. We're told to not worry about the function bodies themselves. We're only interested in the signatures for now, and encouraged with, if anything, this is a good way to peek ahead to future exercises. So we're expecting syntax errors, specifically in the type signatures, which we do have on line 17 here, as pointed out by Rust Analyzer. If we check the hint says that the error message does indeed point to line 17, which is true. So you'll see that the Rust Analyzer inside of my VS Code editor is pointing to line 17 at this specific point, and our error message in the console, if we did say a cargo check or a cargo build, is pointing to the exact same place. So let's read the code. We have a main function with an original price of 51 that prints out your sale price is, and then calls the sale price function with the original price that gets slotted into this print line and printed to the console. Sale price is a function that takes a price, which is an I32, so it's an integer, a fairly large potential integer at that, and it uses another function called isEven with the price as an argument. If it is even, it removes 10 from the price, otherwise it removes 3 from the price. IsEven is defined as a function that takes an I32 and returns a Boolean. If you've never seen this little percent operator here, it's the modulo operator, and it will detect if this number is evenly divisible by this number, which is 2. So if num modulo 2 is equal to 0, that means 2 goes into number cleanly with no leftovers. What we really need to do here is declare what return type this should be. So because we're accepting an I32, I'm going to use I32 as the return type, which is exactly what we needed to do. Rust requires that we include types in our function signatures, not because it can't infer what's going on, but because it provides way, way, way better error messages if we do. So while Rust, the compiler, if we didn't provide types for the argument here and the return type, it could figure out what we meant, but it might figure it out through a chain of 5 function calls and result in a very confusing error message. So that's the core reason why we need to specify the types whenever we define a function. And I really agree with this decision because I've seen what happens when there is too much type inference and how hard those error messages can be to read. So just remember that the Rust compiler is very powerful, but sometimes we would rather cut off those errors early to get better error messages. In functions 5, we're back to not having a description, so we kind of just need to get this to compile. In this case, our program has a main function that declares a variable answer that is the result of calling square on the number 3, and then prints that answer out. The square function takes a number that is an i32 and returns an i32. The compiler tells us that we have mismatched types. Specifically, in the return type of the square function, we expected to return an i32, but we found that we actually are returning 2 parentheses. This is our first encounter with this 2 parenthesis type, which is called unit. This 2 parenthesis type effectively means nothing. So by default, all functions will return this unit type, but we've declared that we're returning an i32 instead. This is also where we encounter for the first time that Rust is an expression-based language. What that means is if we have this function square, we have a number of expressions inside of it. The last expression in the function body becomes the return type. And in Rust, a semicolon isn't just superfluous syntax. What it's saying is take the expression before this and throw away the result. So normally number times number returns a number. So if we have an i32 times an i32, we would get back an i32. But because we have this semicolon here, it's taking the return value, the i32 that comes out of this expression, and just throwing it away for us. This is really convenient, but it means that if we accidentally include a semicolon when we meant to return this value, we'll return unit instead of returning that value. So we have 2 options here. One is much more classic and probably what you're used to doing in other languages, which is to type return and to keep the semicolon around. So we're saying return this expression, and if we save that, we'll see the square of 3 is 9. The other way to handle this is to remove the semicolon and not add return. This also works because the last expression in a function body will be the return value. We'll see this even more as we go on. If1 is the first exercise that requires us to write a function body. We've got this function bigger that accepts 2 integers, a and b, that are i32s and returns an integer, an i32. The instructions say complete this function to return the bigger number. Don't use another function call and don't use additional variables. Now what they want you to do here, which is perhaps evident from the name of the exercise itself, is use an if expression. Like we talked about in the last exercise, we have defined this function to return an i32, but currently we're returning nothing. There's nothing in this function body, so we're returning unit. So because Rust is an expression-based language, common constructs like if, which we're used to being statements in other languages, actually get to return values. So in this case, the logic that we have to implement here is if a is greater than b, then we return a. If b is greater than a, then return b. If they're the same, it doesn't matter because they're both the same, so it doesn't matter which one we return. So in this case, I've chosen to do that by saying if a is greater than b, then we'll return a, otherwise b. And remember that Rust is an expression-based language. If is an expression in Rust, not a statement. So inside of the body of each of the ifs and the else clauses, the last expression inside of this body will get returned. In this case, if a is greater than b, a returns from if. Otherwise, b returns from if. And because this if expression is the last expression in the function body, any value that's returned from this if will get returned from the entire function. Now, they do want to introduce if expressions in this exercise, but there is also a better way to write this function, and that's like this. Integers like i32, or really any other type, have functions that are associated with them that we can use. In this case, if we have an i32, we can use the max function to return the maximum of one of 2 values. So this bigger function is actually already implemented as max, and we can just use that anywhere we want to. Now you'll notice that for this exercise, the code is compiling, and we get an additional message that the tests pass. That's because in the bottom of this file, we have a bunch of tests. Testing is built in Rust, and it's something that we'll cover later in this video. So I'm not going to cover it now, but feel free to read this code if you want. The instructions for if2 are step 1, make me compile, and then step 2, get the bar for fuzz and default to baz tests passing. So we've got one function here that's called foo if fizz. I don't particularly love using foo and fizz and bar for these. We'll charge ahead anyway. The foo if fizz function takes an argument called fizz-ish, that is a string slice, and returns a string slice. We haven't covered what string slices are yet, but we'll get to that. The body of the function attempts to use fizz-ish and test to see if it's the same as a string slice fizz, and if it is, return foo, otherwise return 1. Now, this specifically doesn't work. We already covered that if is an expression, which means that we have a return value from each of the blocks for the if block and the else block. But you'll notice that in all of the functions that we've had so far, we've only had a single return type. Whether that's an i32 or u8 or a string slice, it's always just one return type. That also holds true for expressions. So if we want to return a string slice from the first block, we have to also return a string slice from the second block. So to get this to compile, all I have to do is change the 1 into a string. And now we get what is our first failing test output. Now this is all white text because of the way that the Rustlings CLI is written, but if you run cargo test on your own, normally this output looks a bit better. We can see that Rustlings ran 3 tests. Those tests are in the tests module, the foo for fizz test, the default to baz test, and the bar for fuzz test. The first test passed, and the second 2 failed. Each of the failures gets their own output. So the default to baz test printed out some result, basically. In this case, our program panicked at an assertion on line 34. So if we look at line 34, we can see that there's a default to baz. There's this assert equal macro that we haven't covered yet. It calls our foo if fizz function with some input and gets some output as the second argument. This assert equal macro is testing to see if the output from this first function is equal to the second argument that we pass in. If they're not equal, then it panics and we get the output that we see above, where the left side is the string 1 and the right side is the string baz, which makes sense because we just made the string 1 be the return type for our else clause, and we're testing to see in this test whether that output is equal to baz. So in this case, we kind of have to read the tests to figure out what our program should do because Rustlings doesn't really tell us what our program should do. So the first test is passing, the foo for fizz test. If we pass in fizz, we get foo. If we pass in fuzz, we should get bar. If we pass in literally anything else, we should get baz. So if we use the if expression that we're given here, we can do if fizzish equals fizz, we get foo, and we can continue this to say if fizzish equals fizz, then we return foo. Otherwise, if fizzish is equal to fuzz, then we return bar. Otherwise, we return baz. Now this is all fine and well and good, and this works, but I'm going to show you another way to do this. Instead of using an if expression, which you might be more familiar with in other languages, Rust contains a keyword called match. Now fizzish is a string, so if we match on a string, we get to do a bunch of tests on the left-hand side here for values that that string could be. So it's the same as doing this if that we have. If fizzish is fizz, then we execute the right-hand side. In this case, it's just returning foo. If fizzish is fuzz, then we execute the right-hand side. It's returning bar. We also have this special underscore, which is in any other case, we return baz. So while not the point of this exercise, I think it's a really nice spot to introduce match because of how well it fits this particular problem. We can match on fizzish, test against a value. If it fits, then we return a different value. If it doesn't fit, then we fall through to the next case, and so on and so forth until we're done. The if expression totally works, so if that makes more sense to you, feel free to keep using it, but you'll also see match very often in Rust code. Quiz 1 is a quiz for the variables, functions, and if expressions sections. The prompt goes, Mary is buying apples. The price of an apple is calculated as follows. 1 apple costs 2 Rust bucks. If Mary buys more than 4 apples, each apple only costs 1 Rust buck. Write a function that calculates the price of an order of apples given the quantity bought. And we don't get any hints this time. What we do get is this commented out function. So let's uncomment that so that we have our function, and then scroll down to take a look at the tests. We can see that the calculate price of apples function passes in some integer. The integer seems to be some value with a max of 80, it looks like. So pretty much any integer type will work for us. And the return value seems to be an integer as well. So we're passing in some integer, calculate price of apples, and we're returning some price that we're testing against another. So in this case, I'm going to choose the types U8. So the calculate price of apples function will take an argument called numapples, that is a U8, and return a U8. So in this case, even though the amount of apples stops at 80, theoretically, we could buy as many apples as we want. So I'm going to use a U32 for the type, which means that calculate price of apples takes an argument numapples, which is a U32 type, which is a potentially very large unsigned integer. So this number is from 0 above all the way up to something that is way more apples than any one person could buy. And we also use the arrow to define the return type, which is going to be a U32. So from here, we can start translating the requirements. For example, the cost might be 2. But if Mary buys more than 40 apples, each apple only costs 1. So maybe we do an if expression. Because if is an expression, we can test to see if numapples is greater than 40 and return a 1 if it is, and a 2 if it's not. Because if is an expression, we can put the return value of that expression into a variable. So we can define cost as the result of this if expression, and then put our semicolon on the end. And for our final expression in our function, numapples times cost will be the return value. So because Rust is expression based, and if is an expression, the last expression in each of these blocks will be the value returned from the if expression, which we can set in a variable called cost that we can then use in our calculation to calculate the price. And because numapples times cost is the last expression in the function, that is the value that will get returned from this function. And that finishes off quiz 1 and the first couple sections of Rustlings. Congratulations! Why don't you grab yourself some water and we'll get started on the next exercises. Primitive types 1 introduces the Boolean type for us. We're instructed to fill in the rest of the line that has code missing, which is line 15. If we look at the program, we've got a main function, and we've got a variable declaration that says is morning equals true, if is morning, which is a Boolean value, then print good morning, and we have to complete basically the exact same code below it. I'm going to also declare is evening to be true because I want to see the output, and we see good morning and good evening on the left-hand side. This exercise is that simple. There are no tricks. It is just the fact that Boolean values exist, and this is what they look like. Similarly, primitive types 2 introduces the character type. Our main function shows us, again, a set of code that we're going to exactly copy for our own implementation below it. Characters in Rust are defined with single quotes around them. So on line 21, I'll choose a character that is called your character to match the variable name on line 24 and 26 below it. And I'll use a single quote to set R as my favorite character, R for Rust, of course, because, you know, my name is C and they already use C. And if I save this, we'll see that it compiles. But let's take a slightly closer look at this code. Characters are individual characters. So if we take the R that we typed and we put in another character here, Rust is going to let us know that that's not valid. And it says that a character literal may only contain one code point. Now, unless you're really into strings, it doesn't really matter what a code point is. All strings in Rust are UTF-8 strings, and characters require that they are only a single code point, which in our case, because we're using an English alphabet, just means any character. So that means that single quotes define a character and double quotes define a string. In primitive types 3, we have to create an array with at least 100 elements in it where the question marks are. Now, before we actually do that, I do want to mention that an array in Rust is not the same as an array in JavaScript. If you're looking for a growable array, something you can push things into, like you're used to in JavaScript or other languages, the type that you're looking for is a vec, that's VEC, or a vector, not the array. An array is a fixed sized set of elements. So if we define an array that has 100 elements, this array will always have 100 elements. The difference between this style of array and what a vec is, or an array in other languages, will become more apparent as you use Rust more. But suffice it to say that most of the time, if you're looking for an array as you would find in JavaScript or some other language, what you're looking for is probably a vec, not this type of array. That said, there is special syntax for constructing arrays. On the left-hand side here, we have the number 0 with a semicolon, and then the amount or size of that array. So we are creating an array of 100 elements filled with zeros. And of course, we can change that number to be as big as we want. So if we do dot length on this array and test if it's greater than or equal to 100, 1000 is going to print out, wow, that's a big array. Whereas 6 is going to print out, meh, I eat arrays like that for breakfast. Primitive types 4 wants us to get a slice out of an array where the question marks are so that the test passes. So we've got a test here that's called slice out of array that defines an array with a number of values. So 1, 2, 3, 4, 5. This is just as valid a way of defining an array as we saw in the last exercise, but this defines a 5-element array. We then need to replace these question marks so that we only get the elements 2, 3, 4. Now we can do this with a range where we specify that we want the elements from 1 to 4 out of A. This will give us the numbers 1, 2, and 3 in our range, which are the indexes that we're looking at for the numbers in A. So if we're looking at indexes 1, 2, and 3, that will give us the numbers 2, 3, and 4. Now this results in an array that doesn't have a size known at compile time, which is one of the difficulties of working with arrays. But that's really easy for us to fix because we don't need the actual values from this array. We only need to look at them. So if we use a shared reference, you can see that the type for nice slice changes to a shared reference of I32s, whereas A is a 5-element array of I32s. Now what I just showed you were called type annotations, and they're a Rust analyzer feature, not code that you need to write inside of this file. So if we look at a shared reference to the values 2, 3, and 4 inside of the array A, we're basically opening a window to those and storing that window inside of the nice slice variable, which we can then compare against a different array of 2, 3, 4. Now this will feel a little awkward because it's the first example of a slice. It's the first example of using the ampersand, but we'll cover that in more detail as we move through the other exercises. In primitive types 5, we are told to destructure the cat tuple so that the print line will work. So the print line is looking for two variables, name and age, that it's placing into these two positions in the template string. Cat is defined as a tuple that has a string in the first slot and a number in the second. While the arrays that we just looked at all need to have the same type for all of the elements, tuples are different in that way specifically. The elements of a tuple can all have different types. And similar to destructuring in other languages, we can use the tuple syntax and give names to each of the positions inside of that tuple to destructure from cat, which is a tuple, into these two values. And this is checked by the Rust compiler. So if we mistype this and we put parentheses around just name, we will get warnings. In primitive type 6, we need to use a tuple index to access the second element of numbers. So we have this function called indexing tuple that has a variable called numbers, which is a tuple of 1, 2, 3. We need to replace these question marks to put a value into second, which is going to be the number 2. We can index into a tuple very similarly to the way that you would index into an array or a vec by using an index value after a dot. The tuple indexes are ordered from left to right. So 1 is at index 0, 2 is at index 1, and 3 is at index 2. So numbers.1, which is an index, refers to the first index, which is the number 2. In vex1, our task is to create a vector which holds the exact same elements as the array A. We have this function arrayNvec, which returns a 4-element array of I32s in the first element of a tuple, and a vec of I32s as the second element in a tuple. We can see the tuple constructed on line 13, with our array in the first position, and the vec we haven't written yet in the second. There's some special syntax we can use to construct a vec. So if we use vec with an exclamation point, the vec macro, we can then use square brackets to declare a vec in the same way that we would declare, say, the array above it. In vex2, we're given a vec of numbers. Our task is to complete the loop so that each number in the vec is multiplied by 2. So we have this function vec loop. We define a mutable variable v, which is a vec of I32s, and we're going to return a vec of I32s. So we're taking in ownership of this vec, and we get to do whatever we want to it. In this case, we iterate over all of the items in the vec mutably. So we're looping over each item with the ability to change what that item is in that vec. We use a for loop to iterate over that iterator. Again, we'll cover iterators in more detail later in these exercises, so don't worry too much yet. I, in this case, is going to be each element of the vec, so it does help for me to bring up the type annotations to explain this, so I'm going to do that now. we can see that I is a mutable reference to an I32. We haven't really talked about ownership and borrowing and references and mutable references yet, so don't worry if this feels a little bit confusing. We will cover it again later. In this case, I is a mutable reference to an I32, which means that we're holding something that will tell us where that I32 lives so that we can get access to it and change it. This ampersand means we have a reference here. So to actually get to that value so that we can change it, we need to dereference. We can dereference with the star. So if we dereference that mutable reference, we get access to where the value is, basically. We get access to the underlying value. And we can set that underlying value equal to something. In this case, we multiply that underlying value. So we get to that value by dereferencing again. And then we multiply, which confusingly uses the same character as dereference. And then we multiply by 2. So it's a little bit unfortunate that we're doing multiplication here, but the first star is a dereference operator on I. The second star is also a dereference operator on I. And the third star is actually a multiplication operator. Depending on what you're used to seeing, this could also be a little bit more clear. If we dereference to the value, we can use the times equals operator with the number 2, which does the same thing that we just said. We're setting this value to this value times 2. If you've never seen this operator before, it's very similar to the plus equals operator or any of the other similar operators that you may have seen in other languages. Don't worry, you don't have to use it if it doesn't make sense. You can write it the longer way, which is why I showed you the longer way first. At the end of this function, after we've mutated these values, we return v again, which returns this vec. We also have a second function here called vecMap. And again, I'll repeat that we haven't gone over iterators yet, so this is likely going to be very new for you, but we will go over iterators again in future exercises. So if we take our vec, v, and we create an iterator from that vec, that allows us to run a function that maps over all of the items in that vec, and then collects them back into another vec. So in this case, map is serving the same function as our for loop. It gives us each of the numbers in turn, which we can then just do number times 2. And because again, Rust is an expression-based language, the last expression in this block gets returned from this closure, which sets that value for any future processing. In this case, all we do is collect. Collect knows to collect into a vec because the return type is a vec. Remember, I said Rust's inference is extremely powerful. So collect knows from the return type because this expression is in the return position or the tail position or the last position or however you want to say that. Collect knows to collect into a vec here. Once you dive into iterators more, this will feel much more natural, I promise you. Into move semantics 1. Move semantics 1 doesn't have a description, so we kind of just need to get this program to compile. If we look at the error message says we cannot borrow vec1 as mutable, as it is not declared as mutable. And it gives us vec1 on line 9 and gives us some help text. Consider changing this to be mutable, because later on line 13, we're trying to push into this vec. So if we declare a vec on line 9, which is immutable by default because that is Rust's default for variables, and on line 13 we use the function push, which requires changing that vec, requires mutating that vec. Rust knows that because we haven't declared this as mutable, that we're not allowed to run this function yet. In this case, we can declare vec1 as mutable because we do want to push this 88 on top, and that's enough for us. Move semantics 2 has a very similar program, and it says make me compile without changing line 13 or moving line 10. So line 10 needs to stay here, and we're not allowed to change line 13. So let's take a look at the information the Rust compiler is giving us. It says we've got a borrow of a moved value vec0. So vec0 is defined on line 8, and we pass it into fill vec. And let me save this to make it a little easier to see. So what we've got is vec0 being passed into fill vec and then being used on line 13 in this print line to print out the length and the values. The Rust compiler helpfully informs us that we define vec0 here on line 8, that we move that value into fill vec on line 10, and then we try to borrow it to get the length again on line 16. So Rust by default has something called move semantics, where if we have a vec here and we pass it into fill vec, the function signature for fill vec takes a full vec, like just a regular vec, and it takes ownership of it, which means that we're giving the variable vec0 to fill vec,
and we're moving that value into the function. So we can't actually access vec0 after we give it to fillvec because fillvec is taking ownership of that value. So what do we do when we have a situation where we want to pass this vec into fillvec? Fillvec returns a completely different vec, and then we also want to print out the values vec0. Well, one option is we can pass one copy or one clone of the vec into fillvec, and then we can keep the vec0 around for later usage in our root scope. This allows us to keep the original vec0 around while passing in basically a clone or a copy of that vec to this other function, which can then take ownership and do whatever it wants to with that data. Anything it does to this clone won't affect the original vec, so we can still use our original copy to print out on line 13. When you run into borrowing issues, especially early on using Rust, don't be afraid to clone. The language that you're coming from, whether it's JavaScript or something else, is likely already doing a bunch of these clones, and you don't even realize it. Just because Rust makes it apparent when you are cloning doesn't mean that you need to optimize that clone away. Always try to adhere to the semantics of your program first, and then optimize after measuring benchmarks later. It is always easier to remove an extraneous clone than it is to deal with a bunch of lifetimes and references that you've tied yourself into a knot over. Move Semantics 3 gives us a very similar program to Move Semantics 1 and 2. The instructions we're given are to make the program compile without adding new lines, just changing existing lines. So if we take a look at the error message, we can realize that fillvec is different than the fillvec that we've had in Move Semantics 1 and 2. It doesn't create an additional vec. It uses the vec that we passed in and tries to push values into it, which, as we've previously experienced, requires making this variable mutable. And in fact, that's exactly what the error message is saying that on line 21, we can't push in because we can't borrow the vec as mutable, because push requires borrowing the vector as mutable before it returns the vec back to us. The suggestion is making fillvec take a mutable vec. And in fact, that is the only change we need to make here. It's important to note that we are taking ownership over this vec anyway. So the mute here is only us telling the Rust compiler that we are actually going to mutate this, and to act and check to make sure that we follow the rules of being able to mutate stuff. We already have ownership over this vec, so we can do whatever we want to it. And giving this extra information to the Rust compiler, whether this variable is going to be mutable or not, is us telling the Rust compiler to check our work and make sure that we haven't done any mutable access to a variable that is immutable, or that we haven't tied ourselves in a knot trying to mutate a variable from multiple different places at the same time. Move Semantics 4 is basically the same program again. We're instructed to refactor the code so that instead of passing vec0 into the fillvec function, the vector gets created in the function itself and passed back into the main function. If we look at fillvec, we can see that there's no arguments being passed in the function signature. So we can remove the vec0, and we will remove the vec0 on line 10 as well. On line 31 then, we'll create a new empty vec and use that vector instead to push values into and return. Note that we're no longer really filling some vec that we've passed in. We're just creating a new vec and passing that back. In Move Semantics 5, we're given a program, and we're told that we need to make it compile by only reordering the lines, but not adding, changing, or removing any of them. What this means is that we need to rely on the fact that there are a bunch of mutable borrows happening here, and rely on the information the Rust compiler is giving us to make sure that these mutable borrows happen in the right order. So going through the code, we have a mutable variable x that is equal to 100. We have a new variable y that is equal to a mutable reference to x. The next line is the declaration for y, which is defined as a mutable reference to x. The line below that is defined as z, also a mutable reference to x. Then we mutate x through y by adding 100, and then we mutate x again through z by adding 1,000. Altogether, this program should result in x being 1200, because we define x to be 100, and we define y and z to be mutable references to x. So if we change what y is, that means we're changing what x is. The issue on the left here is that we can't borrow x as mutable more than once at a time. So when we define y as the mutable reference to x, That's fine, but we can't do it twice before we drop it. This makes a lot more sense if you start thinking about references as shared references and exclusive references rather than immutable references and mutable references. The ampersand mute syntax defines an exclusive reference. And when I say it like that, it starts to become apparent why we can't have multiple of them. Because we're declaring that y has exclusive mutable access to x. If y has exclusive mutable access, and it can be the only one to modify x, then z can't also have exclusive mutable access at the same time. So if we reorder these two lines, if we move the z declaration below where we do the work with y, then we have our mutable variable x equal to 100. We take a mutable reference to x, and we store that in the variable y. We dereference y to get at the value of x and add 100 to it. And then y doesn't need the exclusive reference anymore, so it drops it. Then we can give the exclusive reference to z because y didn't need it anymore. And we can add 1,000 to the value by dereferencing z to get at x, resulting in x being 1,200. If I put these files back in order, the way we got them originally, now that we've gone over the explanation, it should be easier to see what's going on here. We define y as an exclusive reference to x on line 10, and we try to use it on line 12. In the meantime, we try to also declare another exclusive reference to x in the middle of when we declare that or give x to y and try to use it. And that's the issue. The issue is that we have an exclusive reference, and before we use it, we try to give it away again. But if we reorder these and we give the exclusive reference and then use it, then y can drop it, which means that we can get the exclusive reference again and then do the same thing again. I think that this example in particular is a little abstract. There's no exterior motivation for why we're doing these additions in different places. So don't worry if that part confuses you. We will go over this stuff again in more detail as we go through the other exercises. The takeaway from this lesson specifically is that if you see ampersand mute, think about that as an exclusive reference. This thing has exclusive special ownership over this thing. And if you just see an ampersand, think of that as a shared reference, where multiple things can have access to a shared reference. Only one thing can have access to an exclusive reference. Okay, we've got a program that doesn't compile. We've got no instructions in the file for what to do about it. So let's read the program first. We've got let data equals a string called Rust is great. We call get car with that data. And then we call string uppercase with a shared reference to that data. We've got a comment here on line 15 that says this should not take ownership, and a comment here on line 20 that says this should take ownership. So if we read the error message, we see that there's an issue that is a borrow of a moved value data. Data is the variable we define on line 8. On line 10, we give it to get car because get car takes ownership over the string. So now we've moved that value into get car. And then on line 12, we try to use data again to pass a shared reference into string uppercase. So if we look at the function signatures, we can see that get car is returning a car and string uppercase isn't returning anything. And if we look at the functionality in get car, we can see that on the string we call cars, which you don't know this yet, but I do and I'll tell you, cars returns an iterator that has another function on it called last. That will give us the last item in that iterator. So we're breaking apart this string into individual characters and then getting the last one, which could fail. So we're using unwrap here, which is another thing that we haven't gone over yet. What this means is that we don't actually need ownership over this string. We can take a reference. So if we specify get car as a reference, the original borrow of moved value goes away because what we're doing here is we're taking data, we're passing a shared reference into get car. So we're saying get car can look at this, but not mutate it. And then for string uppercase, we're doing the same thing. Like you can look at this data, but you can't mutate it. So now we're not moving this data into get car. We're sharing it with get car. And when it's done, we get to keep using it. Now we have a second issue here. Temporary value dropped while borrowed. So on line 21 in string uppercase, we've got a mutable variable data that contains a reference to a string. The error message says, hey, we have a shared reference here. Let's call the lifetime of this reference 1. Now we haven't covered lifetimes yet, but the short version for this exercise is that every time we pass data in a way that is shared with somebody else, there's an owner of that data. So on line 8, we declare the variable data to own this Rust is great string. If we tell somebody else they can look at that string, then this variable needs to live longer than the period of time where that person or that function is going to look at it. So in this case, data owns the string, and we tell getCar it can look at the string, which means that data has to stick around until at least after getCar, because otherwise we can't guarantee that getCar will be able to actually look at that data. This is what a lifetime is. Data in a Rust program lives for some amount of time. In this case, data lives until the end of this main function. So this getCar that uses a shared reference to data is totally fine to do that because we know that this data is going to stick around. Going back to string uppercase, we're passing in a reference to a string, and we've labeled that lifetime 1. So it's lifetime 1. We then take our variable, data, inside of string uppercase, and we call the toUppercase function on it. If we go to the Rust docs at docs.rustlang.org, we can go to the string struct. On the page where string struct exists, we can find the toUppercase function. This function returns a string, capital S string. And if we read the description, it says it returns the uppercase equivalent of the string slice that's given as a new string. So we're taking data, which is a reference to a string, and we're creating a new string from that data. This string, this new string, doesn't have an owner. It doesn't live anywhere. So that's what we call a temporary. If we try to reference that string, since that string only lives inside of the toUppercase function, it will be dropped because there's nothing to own it. There's nothing to keep it around. And that's what this means. Data.toUppercase creates a temporary, creates a string that we then try to reference to store inside of this data variable. But because we're referencing it, and because it doesn't live anywhere, it gets dropped immediately. And it doesn't live long enough for us to use data in this print line. Now, there's an additional snag here, which is that data has to be a reference to a string because we've defined it as such. So if we just get rid of this shared reference, data.toUppercase is going to return us a string, a capital S string, not a reference to a string. These are two different types in Rust. And the helpful suggestion, which has been so helpful so far, will tell us to consider borrowing here, which puts us back in exactly the same situation we were just in. But if we read the error message and we find out that we're expecting data to be a reference to a string because of the way we've defined it in this function, then we can remove the shared reference from our function signature. And then our problem isn't in this function anymore. It's in our usage up here on line 12. So we don't want to pass in a shared reference anymore. We want to pass in the actual string because string uppercase is taking ownership of this data, which we can then use to uppercase and create another string and store in data and then print line out. Now, I do want to mention that this is a little bit convoluted. This function could be written in different ways, and it is written this way specifically so that you run into this problem, not because this is how you would do it in the real world. As you write more Rust, you will find out more about these shared references, and you will find out more about ownership, and that's a natural progression of becoming more experienced with Rust. In structs 1, we're told to address all the to-dos to make the tests pass. In this case, we've got 3 different types of structs. If you're familiar with other languages, structs are kind of like typed objects. In this case, we've got the color classic struct, the color tuple struct, and the unit-like struct. To find out how these are used, we do have to look at the tests. So in the classic C structs test, which don't worry if you've never written C, it's irrelevant. In this case, we've got let green equals, some struct is going to go on the right-hand side here, and we'll access fields individually, red, green, and blue. I'm going to use the fields red, green, and blue because those are the fields that we saw in the tests. And the numbers in the tests look like they're from 0 to 255, which to me is very similar to the values that we use inside of CSS and other, which declare red, green, and blue channels as numbers from 0 to 255. This is true, of course, even if you're using hex values for your CSS colors. So in that case, I'm going to choose the number U8 because a U8 is an unsigned 8-bit integer. 8 bits of storage gives us 256 numbers that we can store. and unsigned means that those numbers are going to be allocated from 0 to 255. So in this case, we can let green equals color classic struct, and then use the curly braces to set the fields with their values. In this case, I've copied the values from the test because that's what we're supposed to be doing. If we look at the next test, tuple structs, we see that the access on green is 0, 1, 2 as indexes. The values are the same, so I'll use U8s again, but for the color tuple struct, all we have to do is define the types in the positions that they're going to be used. We've seen tuples before, and this acts almost exactly like a tuple with a name on the front. And indeed, when we use it, we can instantiate this tuple struct by effectively writing a tuple and then putting the color tuple struct name on the front. This allows us to access each of these values in the green color tuple struct by index. So green.0, green.1, and green.2. Finally, we've got unit structs. And unit structs are a little bit special. There's nothing that we need to do to fill out here. If we go back up and we look at the struct, it's a struct that's defined with the struct keyword, but doesn't have any fields and doesn't have any tuple elements. That means that this struct is only really useful as a marker. In game engines like Bevy, we can use unit structs like this as components on our entities to test to see whether they exist on those entities or not. So if we search for all of the entities that have unit-like struct on them, or paddle or player or whatever we want, then we're effectively marking those things as rather than including any sort of data. Instantiating a unit struct is just typing the unit struct name. So to recap, we've got 3 types of structs. We've got a struct that looks a lot like an object with types. We've got a struct that looks a lot like a tuple with types. And we've got a struct that doesn't contain any fields at all. In structs 2, we're told to address all the to-dos to make the tests pass. If we scroll down, we can see the to-dos are actually in the tests in your order. Specifically, it wants us to create our own order using the update syntax and the template above. So on line 38, we've got your order as a little bit of template code. And above, we've got a struct order, which has a bunch of fields and a bunch of types, as well as a function called createOrderTemplate that returns an order with some default values. Now, they specifically mentioned using update syntax. This syntax is very similar to the object rest spread in JavaScript or other languages. In this case, though, Rust has specific rules for how this can be used. It must be the last element in the fields for defining a struct, and we use 2 dots instead of, say, 3. So while we're instantiating this order with a custom name that matches the test and a custom count that matches the test, this createOrder function template returns us another order. And by using this update syntax ... on that order, we're saying any of the fields that we haven't defined, take from this other order that we've already instantiated. So your order now has a name, hacker in Rust, with a count of 1, and all of the other fields are going to be from this order that is returned from the createOrderTemplate function. So the year will be 2019, made by phone will be false, and so on. Structs 3 says that structs can contain data, but they can also have logic. In this exercise, we've defined the package struct, and we want to test some logic attached to it. Make the code compile, and the tests pass. So if we look at what we have here, we've got a struct package with a couple of fields. 2 of the fields are strings, and 1 is an I32. We've got sender country, recipient country, and the weight of the package in grams. This is our first look at the impl keyword. So while we have a struct above called package, we can associate functions with the package type by using impl. This allows us to define functions inside of this block that will be associated with the package type. If we go look at the tests, we can see that the new function, for example, is associated with the package type, and we can access it using this double colon syntax. So package : new, and then we get to just call the function with whatever arguments it needs. I'll also note that even after we call this function on that type, the functions we define are available on any instance of that type as well. So if we define a package from package new, we can also call the isInternational function on that package. And you'll see the new function defined up here, as well as the isInternational function. The hint says the new method needs to panic if the wait is physically impossible. How do we do that in Rust? Of course, that's already written for us, so I'm not sure why it's in the hint. On line 19, we can see the panic macro. The panic macro will crash our program if the weight in grams is less than or equal to 0. When writing real-world Rust programs, you usually don't want to panic, but it can be useful in certain situations. The hint continues for is international, one of the functions that we actually need to fill out. What makes a package international? It seems related to the places it goes through, right? What they mean is that there's a sender country and a recipient country on the package, and if those aren't the same country, then it's defined as international. For calculate transport fees, bigger is more expensive usually. We don't have a size, but something may fit the bill here. So they don't really describe well what they are looking for, but is international is going to take sender country and recipient country, and if they're the same, then it's not international. If they're different, then it is. And get fees takes self and cents per gram, which is a cost. And because we have the weight in grams, we can multiply those two together to get the full cost. The other way you could figure this out is the return type of is international needs to be a Boolean because we're asserting on it in the tests. And the return value for get fees needs to be a number because we're asserting equal on get fees with a cents per gram against a number. So all that means is we need to implement is international and get fees. We haven't talked about it yet, but when we impl package, the arguments that get passed to the function have some special significance. If we pass in a reference to self, what we get as this self argument is the package we're operating on. So down below, when we run package.isInternational, this package is the package that comes in as self here in this function. So we can check self.senderCountry not equals self.recipientCountry, and that returns a Boolean for us. Similarly, for get fees, this is also called on a package that we've already constructed. So it takes a self and the cents per gram. And we can take the weight in grams and multiply it by the cents per gram to get that integer that we need, which is the cost. So the important takeaways here are an impl block for a particular type allows us to define functions that can be called either on the type using package : new or on an instance of the type, in which case we can use the shared reference to self to access the fields of the instance that we're working on. Here in enums 1, we're told that we aren't getting any hints. So we really just need to make this compile. In this case, we've got an enum declaration, which is called message, and the body of the enum declaration is what we need to fill in. In our main function, we're printing out a number of different messages. So quit, echo, move, and change color are likely what we need to define inside of message. We can do that by putting quit, echo, move, and change color inside of the message body. These are called variants when referring to enums. So we can say that this is the quit variant of the message enum, or the echo variant of the message enum. Currently, you can consider all of these variants to be unit structs, like we talked about in the structs exercises. Enums 2 introduces us to the fact that enum variants can carry data. Again, we aren't giving much instruction here, but we have an enum called message. We've got an impl block on message called call that takes a reference to self and prints self out. So in this case, if we call on a variant, this will print the variant out. And in our main function, we've got a list of messages, 4 of them in fact, 1 for each variant that we need to construct. And then we loop over all of those messages and we call on them. So if we inspect how these messages are being constructed, that will tell us what type definitions we actually need to use for this enum. So in this case, message move has 2 fields, x and y, that are some integers. In this case, I made them i32s. So move can be defined similarly to the same syntax that we used to define a struct with fields x, which is an i32, and y, which is an i32. Echo is a tuple struct that holds a string, so we can use the tuple syntax to specify the string inside of this variant. Change color similarly is a tuple, so it's a tuple of 3 U8s, and quit is still a unit struct, so it doesn't take any fields. Enums 3 tells us to address all the to-dos to make the tests pass. We're faced again with an empty enum message that we need to fill out, but this time we're given additional structs. So we've got a point struct that has fields x and y that are U8s, and we've got a state struct, which includes a color, a position, which is the point, and quit, which is a Boolean. State has an impl on it that defines a number of functions, most of which, all of these top ones, we don't need to change, and one of which we need to fill out. So if you look around the file a little bit, you'll notice that there's a set of messages that are similar to the messages that we saw before, change color, move, quit, etc. and there are functions that match up with each of those variants. So this process function takes a message, as well as a mutable reference to self this time, and translates each message into one of these function calls. In this case, each of the variants are defined by their usage down here. So if we read the usage for each of these, we can see that, for example, change color isn't just a tuple struct itself, but contains an actual tuple inside of it. This is different than the type we had earlier, which didn't have these extra parentheses. Move contains a different struct called point, while the other two variants are the same as what we had in the last exercise. So inside of process, I'm going to use a match on message, and I'm going to show you a little trick here. Rust Analyzer, for me, the shortcut is command dot, but Rust Analyzer is capable of filling out these match arms for us so that we don't actually need to type them. So if I want to match on message, I can activate Rust Analyzer and choose the fill match arms quick fix. And that immediately writes out all of the message variants with stubs for each of the right-hand sides. In this case, each of the variants corresponds exactly to one of the functions, and the value inside of each of these structs, especially the tuple structs, gets passed in directly to whatever function is required to be called. So the move point gets passed into move position point, change color, color gets passed into change color, color, and so on. Strings1 wants us to make this program compile without changing the function signature. The program we have calls a function called currentFavoriteColor and then prints that answer out. The function currentFavoriteColor returns a string, and what we have here looks like a string, but the insight is that Rust actually has two different string types. The compiler, of course, knows this and gives us the right help text. So on line 12, we expected a return type of string, and on line 13, we found a string slice. And it gives us a little bit of help that says, hey, you should use toString here instead, which is the correct answer. Now, you'll become more familiar with the difference between a capital S string and a reference to an str as you get further along in your Rust career. For now, suffice it to say that a capital S string is an owned string that you can mutate, you can push onto, you can add to, you can do whatever you want to it. An str, which is almost always used with this shared reference in front of it, is a string literal, or a reference to a string literal. This second type, the string slice, exists because when we run and compile a Rust binary, this string will get placed into that Rust binary verbatim, whereas a capital S string is the kind of a string that we would create at runtime. Now, in many cases, you can turn a capital S string into a string slice by passing around references to it or whatnot, but note that there is a difference, and that's why string literals aren't considered capital S strings, because they're stuffed into the binary, and that's where we're referencing them from. So if we were able to mutate one of these string literals, we would be mutating the binary itself, which we can't do, or at least, so if we want to return an owned string that we can play with at runtime, we have to use the toString function on our string slice. Strings2 also wants us to make this program compile without changing function signatures. So we've got this function is a color word that takes a string slice and returns a Boolean. It compares that string slice to some string literals, green, blue, and red, which is totally fine. And in our main function, we create a capital S string from a string literal and store that in the word variable. So word is a capital S string, and is a color word needs to accept a string slice. The Rust compiler here is super helpful because it knows that you can convert from a capital S string to a string slice using the ampersand. So on line 9, it says arguments to this function are incorrect, which points to is a color word, and the argument word was expected to be a string slice, but found struct string. The help text says consider borrowing here and shows you the ampersand in front of the word. As it turns out, that is perfectly accurate. You can take a capital S string and pass it to any function that requires a string slice by using the ampersand. Strings3 doesn't include much instruction at the top of the file, but it does have a number of to-dos inside of each of these functions that we need to fill out. Now, the functions that we need to implement are remove white space from both ends of a string, add space world exclamation point to the string, or replace cars in the string with balloons. So let's start with trim, and let's go back to the string docs. In this case, if I just search for trim because they've named it correctly, or at least named it very relevantly, you can see that the trim function on strings returns a string slice with leading and trailing white space removed. And of course, because this function returns a string slice and not a string, we have to add toString at the end to satisfy our function signature. The reason trim doesn't need to give a string, a capital S string, back from its implementation is because we're not actually doing anything to the actual data. We're just changing our view of it. So you can imagine that if we have a string or a string slice, .trim then returns us a view into a shorter version of that string. So you may be given a string slice like this, which is hello with a bunch of space on the end. And all trim is doing is saying, instead of going from index 0 to index 9 in this string, we're going to go from index 0 to index 5. So we're getting a view into the other data, which is why this can return a shared reference to that view into that data rather than needing to create its own new string. Of course, we want to return a string anyway, so we toString it. Adding world to the end of a string is a little bit of a confusing way to word this because we're not mutating anything here. There's no mutation in the function signature. There's no shared mutable. There's no mutable references. There's nothing here that says that we're mutating anything, which means that basically we need to take the input and construct a brand new string. The way this is typically done in Rust is using the format macro. So you'll remember the curly braces from when we used println. This functions the same way, except that here we have a new usage of it. So this template string, if we put the input keyword or the input variable inside of the curly braces, we'll put input exactly into this spot. And we don't need to use a positional argument afterwards, so we wouldn't need to write input here. And then the rest of the string functions as expected, with space world being added to the end of the input. And this creates a new capital S string rather than mutating anything. The third function is replace me, which wants to replace cars in the string with balloons. Again, if we look in the string docs and we just search for replace, the function comes right up. There's a function signature here, and it says it replaces all matches of a pattern with another string. We can completely ignore reading the function signature and check out the example because the Rust docs are pretty good about this. In this case, we've got s.replace, the old string with the new string. And the string was this is old, and now it's this is new. So that's exactly what we need to do. So on our input string, we can .replace cars with balloons, and we're done. This is more of an exercise in reading the documentation and finding out what functions are available to you on different types, which is a skill I highly encourage you to practice. If you ever feel like you need to do something with a string or a number or another type, maybe go to Google or go to the Rust language docs or go to the crate docs for the thing that you're working with and just see what functions are around. In the Rust docs specifically, there's this sidebar here, which will show you all of the methods on any specific type and all of the traits that are implemented and other things. So if you ever have a use case, make sure you go just check the list of functions that are available to operate on that type. There may be one that already does exactly what you need. In strings 4, we're given 2 functions and a ton of values. Our job is to replace all of these question marks with the appropriate function. Now, the way this is set up is that if we pass in a value that matches the argument type for each of these functions, then the program will compile. So for example, if I comment out everything here, and we've already talked about string literals being string slices, I can put the string slice function here. And because the string slice function accepts an argument that is a string slice, this will compile. Now I've commented out everything else, so it looks like we've passed everything. But let's take a look at what happens if we put the string function here. We'll get a mismatched types error. So the way this is set up just so happens to work in our favor. We've got 2 functions. One is called string, one is called string slice. Whichever value we're passing into that function needs to match the argument or the program won't compile. So let's go through these one by one. First of all, we have a string literal. String literals are string slices. This is because the string literals are embedded into the binary themselves, and we are looking at a view of that data. A string literal with toString called on the end creates a capital S string. So this will be the capital S string. Similarly, if we use the associated function from on the string type, we will also be creating a capital S string. ToOwned and into are 2 functions that we haven't covered yet at all, but suffice it to say that these both result in strings as well. Now, one thing that I'll note is for into, it could be a string or a string slice, which is one of the things that makes this exercise a little bit confusing, because string and string slice are both applicable for niceweather.into, because into is trying to convert into whatever type we want. The format macro always returns a capital S string, and if we use a shared reference on a string that we've created, capital S string from, here we're creating a string from ABC, but we're also taking a slice from 0 to 1 of it and returning that shared slice. So this is a string slice. Hello there.trim, which is a string literal with .trim being called on it, is a string slice, as we actually discovered earlier when we looked at the documentation. This is because to remove the white space from the front and back of a string, we aren't actually mutating that string, we're just changing our view of the string. So you can think of this as being indexes from 0 to 10, let's say, and instead trim gives us back a string with indexes from 2 to 8. Happy Monday is a string literal, which is then converted to a string with toString, that we then replace Monday with Tuesday on, also returns a string. If you think about this, this makes sense because replace creates a new string that replaces all of the old matches with the new matches. And then finally, we have my shift key is sticky.toLowercase. If there's any change in this string slice that we have as a literal here, such as lowercasing all of the values, then we need to create a new string to put that new data into. So this is a capital S string as well. Modules 1 is our first introduction to modules in Rust. Of course, if you write a Rust program of any sufficient complexity, you will need to spread your Rust code across multiple different files. Modules in Rust specifically aren't tied to file paths. So the modules we'll see in these exercises are actually defined right inside of the same file. In this case, the compiler is telling us that the makeSausage function is private. So on line 19 in our main function, we're trying to use a private function. And on line 12 is where that function is defined. And, we could make that public. So in this case, it's like the Sausage Factory module was in a different file and that we've imported it. So inside of the Sausage Factory module, we'll use pub on makeSausage. Because we've used the fully qualified module path, which is Sausage Factory : makeSausage, we don't need to do anything else other than make this publicly accessible. This is the way that modules work in Rust. All of the modules that we have, say, installed from third parties or defined in our project are readily available. All we have to do is dig down through the module path to get to the item that we want. Of course, there is syntax for shortening those module paths because typing them all out all the time is kind of a waste of time, but we'll get to that. Modules 2 is a little bit convoluted. We've got a main function that prints out delicious snacks fruit and delicious snacks veggie. So we've got the delicious snacks module here, and we've got two submodules inside of it called fruits and veggies that each define their own constants: pear, apple, cucumber, and carrot. In this case, the exercise is asking us to expose one of the fruits as a different name. So inside of delicious snacks, we've defined fruits. We can use self::fruits::pear, which points to this pear const, and we can rename it. In this case, we want it to be renamed fruit. In the other case, I've renamed the self::veggies cucumber const as veggie inside of delicious snacks. So now delicious snacks : fruit refers to pear, and delicious snacks : veggie refers to cucumber. Now, if we look at the compiler information, we still haven't exposed fruit as public. Fruit and veggie are both private constant imports. So we can tack pub on these use statements, which will re-expose them through anybody that accesses them through the delicious snacks module. This allows us to access fruit from delicious snacks. We are effectively re-exporting something from inside of the fruits module inside of the delicious snacks module as a different name. Modules 3 includes a bunch of code that we aren't going to touch. The main function uses something called system time to get now, get the duration since the Unix epoch, which is sometime in 1970, and then does some things with it and prints some stuff out. Now, we could access these items by name through fully qualified module path, but more often than not, we aren't going to do that. What we're going to do is use the use keyword to shorten the module name. So in this case, what I've done is used the use keyword to bring in from standard time all items. So if we wanted to, we could do system time here, and it would say, oh, we don't have Unix epoch though. So I could specify that specifically as well, if I can type. And now we've brought in both of those names specifically. Now, this is the exact same thing as taking these module paths and plugging them in manually here. So standard time, system time now is the fully qualified module path for the now function that's associated with the system time struct inside of the time module inside of the standard library. Similarly, there's a Unix epoch const inside of time inside of the standard library, and we could fully qualify those module paths. But as you can see, that makes our code quite longer when we're actually writing the code that we care about. So we often use use to cut those module paths shorter and bring system time as a name into scope so that we can use it without having to use the full module path. Hash maps 1. A basket of fruits in the form of a hash map needs to be defined. The key represents the name of the fruit, and the value represents how many of that particular fruit is in the basket. You have to put at least 3 different kinds of fruit in the basket, and the total count for all of the fruits should be at least 5. So if we scroll down, we can see the fruit basket function. We've got a mute basket declaration where we need to instantiate our hash map. We've already inserted 2 bananas, and then we need to insert some more arbitrary fruit. In our case, the tests don't specify what kind of fruit, so you could insert Legos or something if you wanted to as well. In this case, creating a new hash map is as easy as doing hash map with the new function. The new function that's associated with the hash map type is an extremely common pattern in Rustlang, and is actually one that we've already experienced in these exercises ourselves. So if you have a type and you're looking for a way to instantiate a new version of it, the new function is probably sitting there waiting for you. Now, of course, we need to insert some more fruit, so I've chosen to insert 2 apples and 2 strawberries, which passes all of the tests. If you're unfamiliar with the concept of a hash map, you can imagine it as, say, an object in JavaScript, where the keys are strings and the values are U32s. And you can see that in the type right here. So the hash map has defined the key value as a string and the value type as a U32. Hashmaps 2 gives us working code, or at least running code, that is not currently passing the tests. It says a basket of fruits in the form of a hash map is given. The key represents the name of the fruit, and the value represents how many of that particular fruit is in the basket. You have to put more than 11 fruits in the basket. 3 types of fruits, apples, mangoes, and lychee, are already given in the basket. You are not allowed to insert any more of these fruits. So if we scroll down, we can see that there's a new enum called fruit with a bunch of variants for apple, banana, mango, lychee, and pineapple. Then our function fruit basket takes a mutable reference to a hash map where the keys are fruits and the values are U32s. It also sets us up a vec of all of the variants for the enum that we can then iterate over. Hash maps happen to have this really interesting API called the entry API. In this case, because we don't want to modify any of the fruits that are already in there, but we do want to insert any that aren't there, we can take our hash map, which is our basket, and we can call .entry with the key name. So we're getting the entry for any fruit. If that entry doesn't exist, we can use .insert to insert some number for that key. And that's it. We haven't touched anything that's already in, but we've inserted 2 for anything that isn't in yet. The entry API is pretty powerful and comes with a number of different functions. We've used a few of these APIs, but we definitely haven't used it to its full potential here. So feel free to go look at more of the functions. Hashmaps 3 is one of the more confusing setups that I've found in the Rustlings series of exercises, specifically because it talks more about soccer than actually programming. But the idea here is that there is a section of code that we need to write inside of this build scores table function. Specifically, we have a hash map of some scores. So team A plays team B, they both score some amount of goals. We're given the name of team 1 and the number of goals they scored, and the name of team 2 and the number of goals they scored. And our responsibility is to, for each team, insert their score as goals they've scored and the other team's score as goals scored against them. So for each entry in the hash map, we have the team name as the key or the string, and then we have a team struct that is the value, which includes the name of the team, the number of goals they've scored, and the number of goals they've conceded. Scores is our hash map. So we're going to use the entry API again, like we did in the last exercise, to grab the value based on the team 1 name key. If it exists, we need to modify it with end modify. If it doesn't exist, we need to insert it with or insert. End modify will give us the team, which we can then access fields on to add team 1 score to goals scored and team 2 score to goals conceded or scored against. Otherwise, if the team hasn't been inserted into the hash map yet, we can set team 1 score for this game as the goals scored and the conceded goals as teams 2's score. And then we need to do the exact same thing in reverse for the other team. So this whole exercise is a way to get you to use the entry API in more depth. Specifically, scores.entry on a hash map will give you either the value that was already inserted in the hash map, which we can modify with end modify, or it will let us insert if one doesn't exist using or insert. And beyond all the setup of goals and teams and scores and things like that, this is all you really need to care about. We have a hash map. We can grab the values via the entry API. We can modify them with end modify, and we can insert them if they don't exist with or insert. There are other functions that we can also call. So maybe go to the documentation for hash map and look for those. But we also mentioned them in the last exercise. So that's going to be it for this exercise. That brings us to quiz 2, which is a quiz on strings, vecs, move semantics, modules, and enums. We've got a set of tests here that use a transformer function that accepts a vec of strings and a command to execute for that string. The output is tested against a string output. So this transformer function is going to accept a vec of tuples where the first element in the tuple is a string and the second is the command. The commands are defined here in an enum, which can be uppercase, trim, or append. And then this transformer is going to have to return a vec of strings. So we're taking in the transformer with a bunch of input and commands. We're operating on each of those, and then we're returning the transformed versions as output. So transformer will take an input argument that is a vec of tuples where the first element is a string and the second is a command enum, and it returns us a vec of strings. We have to include a type for the output, which we can actually do one of two things here. In this particular case, we actually don't need to have a type here because we're returning output from this function, which means it has to be a vec of strings, and Rust will infer that and know that. And then down in our tests module, we have to reach into super, which goes up one level. So we're inside of the tests module here. We're going to use super, which is up into this whole file. We're going to go into my module, which is this module here. And then we're going to reach for transformer, which is an item in my module. And that will allow our tests to run. We could, of course, in this output, specify this as a vec of strings, very much like this. But there's no reason that we have to do that because we've already determined that we are returning it from this function, and we've defined what the return value has to be. So output then has to be a vec of strings already, and Rust can infer that. The transform body itself loops over the input iterated, and we destructure the tuple here. So we get the string and the command for each element in the vec. We can match on the command, and that gives us each of the uppercase, trim, or append variants. In this case, the quiz set us up to mutate vec. So we can do output.push with, in this case, string.toUppercase. For trim, once again, we use string.trim, but the output takes a string, so we have to toString it. And then the append variant gives us a number, which we have to repeat. If you look at the string docs, there's a function called repeat, which we can then pass the number value into. So for append, we have to append bar any number of times. So we can have this string, we do .repeat some number. Our format macro is right here. The variable string goes first, and then the curly braces are for the placeholder for the repeated bars. And we get a string out of format, so we push that into the output. And after we loop over all of those and we push all of them in, we return the output and everything is good. Now we haven't gone over iterators yet, but I do want to show you how this would be done with just iterators and not mutating a vec. So in this solution, we take the input and we iterate over it just like we did in the for loop solution. We can then map over each of the items. So we get the string and the command just like we did before, and we can match on that command in the exact same way that we did in the previous answer. The big difference is that we get to return the values from each of these matches. So in this case, we string to uppercase and it returns as the item. We string trim to string and it returns, or we format and it returns. So we don't have to deal with creating the extra vec and making sure that we remember to push items into it or anything like that. We can iterate over, we map, we change, and we return what we need to return, and then we collect. Collect knows what type to collect into because we've specified, again, the return type as vec of string. So that overall is how I would do this if I was doing it with iterators instead of with mutable vecs and for loops. Now, Rust-Lang doesn't have a concept of null. So you won't find undefined, you won't find null, you won't find any value like that inside of Rust. So that leaves an open question. How do we represent optional values? And there's an option in the standard library, which is an enum, where the variants are either sum with the value or none when there's no value. In this particular example, this function returns how much ice cream there is left in the fridge. If it's before 10 p.m., there's 5 pieces left. At 10 p.m. exactly, somebody eats them all, so there's no more left. And of course, this is a 24-hour system because we're using a U16 to represent the time of day. So 10 p.m. is going to be 22. So there's a test down here that we're supposed to fix. Now, because this test actually includes something that won't compile, I do need to comment it out. And we can go back up and we can look at the code that implements the time of day. So this maybe ice cream function takes the time of day and returns an option U16. In this case, I've gone with if the time of day is less than 10 p.m., then there are still 5 items left in the fridge. Because we're using a U16, I know that will never go below 0, so we don't have to worry about negatives here. It won't go below 0 because a U16 can't represent negative numbers. It starts at 0 and goes up because it's an unsigned 16-bit integer. In that case, we use the sum variant of the option enum to return that there are 5 pieces of ice cream still left. And then we continue our if expression, checking to see if it is past 25 hours, which they explicitly call out in the tests as needing to return none. So we return the none variant here. And otherwise, it's sometime between 10 and midnight, which means that there's 0 ice cream left. Now, this test is a little bit awkward because if you look at the hint, it wants you to get at the inner value here, but it also mentions that you can unwrap or you can pattern match. So let's show unwrap first. Unwrap will panic if maybe ice cream is none. So if it's 12, we're fine. And we can see the types change here, actually. If I bring the inlay hints up from Rust Analyzer, and you see that the unwrap is on the end of maybe ice cream returns an option type. If I remove this unwrap, you can see that ice creams is an option of U16s. We can get the value out of that option by unwrapping. If the variant is sum, then ice creams will be the U16. If the variant is none that gets returned from maybe ice cream, unwrap will panic and fail the test. And this is actually the behavior that you typically want in tests. You can also pattern match in the same way that we've pattern matched before with if-let, but I don't think that really makes sense inside of a test that you want to fail if anything goes wrong. So I'm going to leave that at unwrap and move on to the next exercise. So for options 2, there is no description on the top of the file, but there are 2 to-dos inside of the file. One is asking for you to use if-let, and the other one is asking for you to use while-let. So the answer for the if-let is if-let sum word. So we're destructuring the word out of the sum, and we're destructuring sum from optional target. So if-let sum equals optional target means if optional target is some word, pull the word out so that we can use it, and then we do a test from word to target. The while-let example is the same thing. But if you notice, we have optional integers, which is a vec of option of i8, i8 being an integer, 8-bit, and then pop, the function, also returning an option type. The combination of an option being the value that we're looking for and option being the return of this function means that we get nested optional types. So we've got sum from the pop and sum from the option inside of the vec. If the pop is successful and we have an item in the vec, then grab the integer and then we do a test. While-let is for loops, for looping, for going through a series of items, while if-let can operate on a single item. In option 3, our job is to just get the code running. So we have struct point, which has an x and a y, and we have let y, which is an option point, equals sum point. So we're constructing sum point here, in which case we actually don't need to specifically type this, but we'll leave it back there. And then we're matching on y to either print out p and x and y, or print no match. We also want to use y after we've done the match. In this case, we don't actually do anything with the y, it just kind of sits there. But the exercise is asking for us to fix the problem without deleting the usage of y that doesn't really do anything. So the compiler is informing us that we're engaging in the use of a partially moved value y. In this case, it's partially moved because we're destructuring the p in here and we're using it. Now we have two solutions to this, one of which is exactly what the compiler is suggesting for us, in that if you look at the type of p, if you use the type inlays that Rust Analyzer provides us, you can see that it's a capital P point. And when I type ref here, you can see that we're getting a shared reference to point. So we're no longer pulling P or point out of the option. We're just getting a shared reference by using this ref keyword. If we set this back up so that it's failing again, we can also match on a shared reference. And you'll notice that that has the same effect. So either way works. We still get a shared reference to point, and we're no longer pulling ownership out of this option to use it here, which means we're not moving, which means that we can continue to use y later. In errors 1, we see errors introduced for the first time, and specifically the result type. The description goes, this function refuses to generate text to be printed on a name tag if you pass it an empty string. It'd be nicer if it explained what the problem was instead of just sometimes returning none. Thankfully, Rust has a similar construct to option that can be used to express error conditions. The similar construct is called result, and it is also an enum. The hint in this case actually does tell us what we need to actually do in this file, so I highly suggest taking a look at it. Our first move is to change this option return type to be a result. Result takes two type arguments, both what the OK value is going to be and what the error value is going to be. In this case, they're both string, but they could be anything. Next, we have to take the none and some values and replace them with something that works with the result. In this case, we've specified that the error is going to be a string type, so we'll use the ERR variant of result to return a string in the case that name is empty. Otherwise, we're okay, and we can return a string using the format macro. Of course, if we look at the test for the error, they have a specific error that they wanted, so we're going to copy and paste that string in instead of what I used. And that's it. So we've got the option type, which can give us some or none, or we have the result type, which can give us OK or error. The option type loses some error information because the error case is just none, while the result allows us to specify more error context, such as a string like we have here. Both of them are enums and they're very similar, although you will often see result for handling errors and propagating error contexts. So errors 2 has quite a bit of writing at the top of the file, but the TLDR is that we have a total cost function here that returns a result. We've got a processing fee variable, a cost per item variable, and then we parse this item quantity, which is a string, as an I32. So there's a lot of text at the top of errors 2, but we can mostly ignore it. Here we have a function called total cost that takes in a string and returns a result. The result success type is an I32, and the result error type is a parseInt error. A parseInt error is something that we get when we use this parse function down here, which we'll get to in a second. So we've got a processing fee variable set to a number, a cost per item set to a number, and a quantity which is parsed from this string. This is how we take a string and turn it into a number in Rust, and we can stick any number type we want in here. In this case, we're using I32. This item quantity.parse returns a result. We then want to use this quantity in a mathematical calculation down here. So quantity times cost per item plus processing fee. In this case, we're all set up to just use the question mark operator on line 27. The question mark operator, if I bring the type inlays back up, is very similar to the unwrap that we saw in a test in an earlier exercise. The question mark operator will take a result, which is what parse returns, and if it's an error, we will return from the function at this line. If it's a success or an OK variant, then that number gets put into the quantity variable. So using question mark allows us to early return from our function if we get an error, or continue if we don't. Now, because this parse already returns the same type as we need to return from our entire function, we could also get rid of the extra quantity as well as the question mark in this case. So if we take item quantity and we try to parse it, and we bring up the type inlays, we can remember that parse returns a result of I32 or parseInt error. Map is a function on the result type that allows us to run a function if the variant is okay. If the variant is an error, this map won't run. So we pass in a closure here. Quantity is the I32 if it's an okay, and then we can do our math. So the type of this whole expression here is a result I32 parseInt error. .map is fairly common for mapping over the success value of a given enum. So while you might be used to seeing map used on something like a vec or an array, you can think of that vec as a container for some values. In the same way, an option is a container for values. So we could map over if we get a sum value on an option, or we can map over on a result value if we get an OK, and we always get the success value here, and we can do whatever we want with it. That said, I really feel like the question mark operator is the primary goal of this exercise. So understand that the question mark operator will take a result for you and unwrap it or return the error from the function. Errors 3 is a program that is trying to use a completed version of the total cost function from Errors 2. However, as we can see from the compiler output on the left, it's not working. So what do we do to fix it? A brief overview of the program shows us that we have some tokens, we have some fake user input, we run total cost on that fake user input, we're using a question mark here to return the error, and then if the cost is greater than the tokens, then you can't afford it. Otherwise, you now have whatever amount of tokens. In this case, all that matters for total cost is that it's returning a result, and we can take a look at the compiler information to verify that. So the issue is that on line 11, this function should return a result or an option to accept question mark. Again, we're using question mark on line 15, which the compiler shows us here, but the main function doesn't return a result. Remember, by default, all functions return unit, which is basically nothing. So we can change the main function to return a result with the same parseInt error that we're returning from total cost, which is the error that this question mark will return. But we still have one more thing to do. The last expression in our main function is this if expression, but that's not really what we need now. We need to return some variant of result. In this case, we're going to return OK with a value of unit because unit is the success case. So we have the OK variant, and inside of that, we have the two parentheses, which we pronounce as unit. This may be a little confusing, but unit is both a type that we can use in this result, as well as a value that we can use in this OK. The main point here being that your main function can return a result. If it does so, it does need to return unit, but it can accept any error type, which allows us to use the question mark operator inside of our main function. Errors 4 starts out with a compiling program that is not passing its tests. The hint and the description in the file don't really tell us what to do, but if we can read the tests, we can kind of figure it out. The type we have here is a positive non-zero integer, which is a type we made up completely, as you can see the struct keyword right here. So we've got a tuple struct that contains a U64. We've also got an enum called creation error that has negative and 0 variants. The impl for positive non-zero integer has a new function that accepts a value that is an I64, not a U64. So I64s could be negative, but U64s cannot. Judging from the return value here, which is a result of either a positive non-zero integer for the success case or a creation error for the failure case, we can see that we probably need to add some checks here to make sure that the value that we're passing in is both positive and non-zero. We can again use if expressions. In this case, we're testing to see if the value is less than 0. If it is, then we return an error variant for the result with a creation error negative inside of it. Otherwise, if the value is 0, then we return an error variant again with a 0 creation error variant inside of it. Otherwise, the value is positive and non-zero, so we return an OK variant with the positive non-zero integer wrapping our value. The positive non-zero integer also needs to be a U64, so we need to cast the I64 to a U64 using the as keyword. Of course, if you want to use match to, you can, using a feature called guards. If we match on the value, we can grab the value in the first portion of the match on the left-hand side, and we can say if num is less than 0, then we continue to the right-hand side. If it's less than 0, then it's negative. If it's 0, then it's 0, the creation error. And otherwise, we catch all with this value, and it's a positive non-zero integer. Very similar to the if expression that we ended up with. There are two things that I want to say about errors 5. One of which is that it uses a bunch of features of the language that we don't even cover until way later, and actually tells you to ignore them completely in this description. And the other is that in real-world Rust, most people don't use this approach. But let's take a look at the approach first. We've got a main function that returns a result. There's some type value here with some box thing and some dyn thing that we need to add to so that we can return errors from this function. The problem is that pretend user input.parse returns a parseInt error, while positive non-zero integer new returns a creation error. So the challenge is, how do we unify these two errors into some return type? So as it turns out, there's a trait from standard error, specifically the error trait, that we can use to unify these two into something that is passable for something that represents an error. I feel like it's pretty important to note, though, that in production Rust software, you'll find either anyhow, err, or mjet these days. Errors in Rust, either in the compiler or in the user experience, are constantly getting better. Anyhow is the oldest trait in this category, while err is newer, but still fairly stable, and mjet is the newest. In all of these cases, you end up using the result type from one of these crates as the return type from your main function. So you never actually use the Boxstein error that we just talked about. You use one of the reporters with the result types from one of these crates, because the error experience gets so much better when you do that. There's nothing wrong with trying to figure out what Boxstein error is and how it works, but since we're skipping basically everything else in this example just to declare the existence of the error trait, I would also suggest, if you're going to do that, skip it entirely and install one of the error handling crates. Then you don't need to worry about something like dyne error or boxing things until you actually want to or need to. Of course, the very next exercise, errors 6, details that using catch-all types like Boxstein error isn't actually even recommended for any of your library code. So you'll find yourself, if you care about the errors and the types that you're getting, you'll find yourself creating these custom error types out of enums. Sometimes you'll wrap other errors like parseInt error, and sometimes you'll create your own error variants inside of this enum. So in this file, we've got a parse pos non-zero error, which can either be creation or parseInt. We've got an impl for that enum, which includes the function creation and a function that we need to write called from parseInt. And then we've got a function called parse pos non-zero that takes in a string and tries to return a positive non-zero integer, or returns a parse pos non-zero error, which is the error type we just checked. And at this point, personally, I find myself wishing that they had used shorter names for these, or at least less similar names. So this parse positive non-zero function takes a string and returns a result. Our job is to remove this unwrap so that it doesn't panic when that integer can't be parsed. To do that, we'll combine exactly what we're doing on the next line with our own implementation of a similar function for from parseInt. We've got this from creation function for the error, right? The custom error type that we're building. And if we create a new positive non-zero integer and there is an error, then we map over that error similar to the way that we mapped over things earlier, and we run from creation on the error that we would get from positive non-zero integer new. Now the new function returns a creation error. So what that means is that this new function returns a result where the error is a creation error, but we want to return our custom error. So we wrap that error using this other function. And all that function does is wrap the creation variant around the error. So we need to write this from parseInt function, which is almost exactly the same as the function above it. The error that we get in this case is a parseInt error, and the error that we return is our custom error's parseInt variant, wrapping the error. And we'll end up using it in the same exact way. So we've got s.parse, which returns a result. The error type of this result, if we bring up the type inlays, is going to be that parseInt error. So we can then run this map error function to map over that error and give us a chance to change it into something that we can return. We do that with this from parseInt function, and we use the question mark operator to return the error if it is an error, or unwrap the value into X if it's not. Now don't worry, because this again is not quite the way that we write production Rust, although it all does technically work, and it is trying to build up into something that is more production ready. The core takeaways here are that to return an error that is some given error of some kind, you can take the functions that produce those errors and you can wrap those errors in your own error type. So this parse pos non-zero error wraps both creation errors and parseInt errors. So if a library consumer of yours, because this would be code that you wrote, wants to use your parse function, they will be able to get back and know which error happened when they called this function, which allows them to do a match on your enum, whether it's a creation or a parseInt error, and respond accordingly, however they need to. Again, we have more sophisticated libraries for creating these arrow types and converting between them these days. So I would definitely start looking into those if this is a thing that you care about. Generics 1 is kind of hilarious because the shopping list program isn't compiling and it wants us to use our knowledge of generics to fix that. Even the hint that we get from Rustlings tells us we need to tell the compiler what type we're pushing onto the vector. But that's not actually true. We can just delete that type entirely and this entire program will pass. Because this code also includes this push is defining what this vec will contain. If we remove that line of code, we do run into an issue where we do need a type annotation because we haven't used it in a way that Rust can infer what we want. But as long as we actually are putting items into this vec, or we're returning it from one of our functions, or we're doing anything else that Rust could infer, then we don't actually need the type annotation here. That said, we can annotate it if we want to. There are two ways to annotate it, actually. One is, again, to just specify the outer container. So we could specify vec as the type, and we can use this little underscore inside of these angle brackets as kind of like a, hey, Rust, figure this out for me. But that's not quite what the exercise wanted us to do either. The exercise wanted us to put string slice in here because those are the values that we're using in push. I just found it very interesting that very specifically, we A, don't need to put a type here at all, and B, don't need to put a type inside of the vec container either. You can, of course, type as many things as you want to in your Rust program, but there are many situations in which you don't have to. Generics 2 says this powerful wrapper provides the ability to store a positive integer value. Rewrite it using generics so that it supports wrapping any type. So right now what we've got is a wrapper with a value of a U32 and some associated functions in an impl block that take a U32 and return self. So it returns a wrapper. If we wanted to use something like a U8 for this inside of this wrapper, we couldn't right now because it's hard-coded to U32. So that's what generics enable us to achieve. If in our struct, we specify that we have some generic T, it doesn't really matter what you call this, call it whatever you want, use a full word if you need to. I'm quite comfortable with single letters, so I'm going to use a single letter here because it can be any type. This is an example of a situation in which we have a truly generic type. There is no concrete object that this represents. It's just, we can put anything in here. So if we use that T as the value, when we define our struct wrapper, then a value is going to be a T. When we define our impl block, we also need to specify that we have the T generic here. We do need to put it in both locations, and then we can use it in our new function. So in new, we're going to accept a value T, and this wrapper is going to wrap that value and return the wrapper itself. And if we scroll down, that's exactly what's happening. In this case, we're using wrapper new, and we're passing in 42 and accessing the value and testing to see if it's 42. We do the same thing with a string slice, and we test to see if it's equal to another string slice. So we can now use this wrapper with any type because we've made the type of the value generic. Here we get to implement our first trait. If you're unfamiliar with traits, traits are a little bit like interfaces. They define common functionality that we can implement across a number of different types. So your task is to implement the trait append bar for the type string. So here's our trait append bar, and here's the scaffolding for where we're going to do our implementation. The trait append bar only has one function, which appends bar to any object implementing this trait. So the way you define a trait is very similar to the way that you define a struct or an impl block. You can define trait append bar, and inside of this block, define what functions a consumer needs to implement to satisfy this trait. In this case, we only have one function. It's append bar. It takes the self and it returns the self. In our main function, we can see this in action. So we create a string from the string slice foo. We call s.append bar on it, and then we print out that result. So we can implement the trait append bar for some other type, like string. We have to implement the append bar function, which accepts self and returns self, which will be the string type. And because it's a string, the implementation here is pretty trivial. We can use the format macro. We can use a display formatter to put the self variable in, and then we just put bar on the end. And this gives us a string that has the value of original self and bar at the end. Traits are one of the ways that you can add new functions to instances of a type. So if you ever need to say, do something to a string that you couldn't do before, you could define your own trait implement that trait for strings, and then if that trait is in scope, so will the function that you've defined. In traits 2, our task is to implement the trait append bar for a vector of strings. It tells us to consider for a moment what it means to append the string bar to a vector, and they've removed all the boilerplate code this time. Luckily, the code that we have for the trait is basically the same as last time. So what does it mean to implement append bar for a vec of strings? Well, it probably means to push that string on, right? But more specifically, if we didn't know that, we could look at this test down here that creates a vec which has a string foo in it and then calls append bar. Foo is then popped twice, which returns bar as the second result and foo as the first. And that's how I knew that we need to append bar to the vec rather than adding it to every string in the vec. In traits 3, our task is to implement the licensed trait for both structures that we have down below, which is some software and other software. The goal is to have them both return the same information without writing the same function twice. In this case, what they're trying to get us to do is implement a default function body for the licensed trait. In this case, we've got the licensed trait that has the function licensing info that returns a string. We can add a function body here that just returns whatever we want it to, and this will apply to both of the structs because we've implemented licensed for both of them on lines 26 and 27. Traits 4, more traits, more traits. Our task this time is to replace the question mark sections so that the code compiles without changing any line other than the marked one. So the only line we can change is line 23, which is a function called compare license types that takes some software and some other software and returns a Boolean. Now this function calls licensing info on both of the softwares, and we know that licensed is the trait that we care about because the licensing info function is defined on the licensed trait. So what do we replace these question marks with? Well, we can replace them with impl licensed or impl, which we haven't seen in this position before, and then a trait name. This means that software and software 2 are arguments that we don't really care about as long as they implement the licensed trait. This allows us to have access to calling the licensing info function on them without really being able to do much else with them. In traits 5, we have the same task. Replace the question mark sections, but only change one line. So the only change we can make is to replace these question marks with something else. Now, inside of the function, we can see that we call some function on the item and then other function on the item. Something else we can see in this file is that there are two traits, some trait and other trait, that are implemented for some struct and other struct. These traits are responsible for the function names that we saw used in our function body. So some function here just returns true, and other function here also just returns true. It doesn't really matter what they do though. What we need is some declaration here that specifies that item implements both of these two traits so that we have access to call both of these two functions. In our case, this is very similar to what we did in traits 4. We use impl in the same position we did. We define our first trait, so some trait, and then we use a plus sign to call in the other trait as well. So item has to implement some trait and other trait. This gives us access to both of the trait's functions, some function and other function, when we are working with this item. Remember that we don't actually know much else about the item, so there's not much else we can actually do with the item. For quiz 3, we've got everybody's favorite subject, report cards. You did good in school, right? Just kidding. This quiz test includes generics and traits. So what we've got here is basically a report card, and the report card for the school district reports grades in numbers from like 1.0 to 5.5, as well as letter grades from like A+ to F-. As a side note, has anybody ever seen an F- on a report card? That's not a thing, is it? So we need to make the changes to report card to include generics so that these two tests, one of which sets up a report card with a grade of 2.1, and the other of which we actually have to change to be an A+, work. So I'll replace the A+ now on what is now line 57 for me because my file just reformatted. And the Rust compiler rightly tells us now that there are mismatched types. So grade needs to be an F32. It found a string slice. So for us, we're going to need to change grade to be G, which is going to be some generic. Remember that we do also need to say that we're going to have a generic G at the end of the name of the struct. Additionally, the implementation will also need the same generic that we're using in the report card. This brings up an issue with the compiler where we try to use self.grade to print something out, which uses the default formatter, which is the curly braces that we've been using for everything else. You can see this on my line 31, where it needs to be formatted into this third curly brace. We have two options to fix this. The first is exactly what the compiler suggests, where we can say that our generic G in our implementation has to implement the display trait, which is what's responsible for taking the variable and turning it into a string for this formatter. And that totally works, but you'll also see a second form of it. The other form you can use is the where clause. So impl G, report card with G, where G implements display. Both of these syntaxes get used, and there really isn't a big difference between them. I find the where clause easier to read and write, so I usually use that, but you can also put the trait bound inside of that first G. And finally, after using tests throughout all of these exercises, we finally get to tests 1, which introduce us into writing tests. So when we build Rust applications, we often want to run tests, right? But we don't want that test code included in our final binary. So we use this configuration attribute macro to only compile this code when we specify the tests. Putting this attribute macro on top of the tests module inside of this file means that this entire module will not be compiled into our binary unless we specify the test flags. In this case, Rustlings is doing that for us, but it also happens when we run cargo test. We use the test macro to specify that any function that we write is a test, because tests themselves are just regular functions. In this case, we're using an assert macro, but there's no value inside of it. So to get the test to pass, I can just write true in here, and we can see that the test passed. If we want it to fail, we can write false. And then we can see all of the output on the left-hand side. We didn't have any successes, so we don't see any of those. We do see the test that we ran, which is you can assert, which failed, and we can see the standard output for each of the tests. We can flip that back to true and move on. Test 2 is the same exact setup, except we use the assert equals macro instead of the assert macro. The big change here is that it will take two values and guarantee that they are the same. So true and true would work, but true and false will not work. And we see the corresponding test failure because they are not equals. But also, false and false will work because they're equal. And we could put any values that we wanted into here. For example, 2 and 2 are equal, so that passes. In test 3, we get to test a function that's already written for us. In this case, it's an isEven function. So the isTrueWhenEven test can be called for isEven with a number like 4. We can do a similar thing to test that 5 is not even. In this case, I've used an exclamation point to invert the response, which means that isEven will return false for 5, but not false is true, so the test passes. I would probably prefer to use assert equals here, but they gave us the assert macro, so that's what I'm rolling with right now. We've talked a little bit about lifetimes so far. In lifetimes 1, the description reads, the Rust compiler needs to know how to check whether supplied references are valid, so that it can let the programmer know if a reference is at risk of going out of scope before it's used. Remember, references are borrows and do not own their data. What if their owner goes out of scope? Of course, that doesn't explain what we actually have to do in this file, but we can look at the compiler information when we try to compile the application to know what we need to do. In this case, we've got some function called longest. Longest takes a reference to some string, as well as a second reference to some string, and returns a reference to some string. It does this by testing to see which one is longer than the other, and returning one reference or the other reference depending on which one it is. The main function for lifetimes 1 is fairly benign. String 1 and string 2 both own their own data. We use longest on both of them, but both of them are in scope the whole time. So whenever we use result, everything works together because everything is still live. The compiler, however, says we're missing a lifetime specifier. And the help text says, this function's return type contains a borrowed value, but the function signature does not say whether it is borrowed from X or borrowed from Y. Consider introducing a named lifetime parameter. So the big secret here is that lifetimes exist whether we've written them or not. And the only reason that we would have to write them right now is because the Rust compiler can't figure out what the relation between the lifetimes is. And what that means is it can't, at compile time, determine whether we're going to use X's lifetime or Y's lifetime just from the definition of this function. At any given time, we could pass in an X value. That X value could be longer than the Y value, and then we would return X. Or that X value could be shorter than the Y value, and then we would return Y. So we need to define the relationship between all of these lifetimes. We can do that by specifying a generic lifetime, the same way we would just specify a generic type. We then name each of the lifetimes. In this case, we're naming them all the same name, which ties them all together. This example doesn't really show the impact that this has, but suffice it to say that by specifying a named lifetime and saying that all of these have to live at least as long as that lifetime, we have successfully informed the compiler that both of these values will at least live as long as the shortest lifetime. In lifetimes 2, we use the same longest function. In fact, we use the same exact set of lifetimes that we already had in lifetimes 1 that we needed to write. But the main function is different. In this case, we define a string which owns its data called string1. Then we define a variable called result and we don't initialize it. Inside of a new block, we specify string2. String2 does own its data, which is great. And then we pass in string1 and string2 as references to the longest function. Longest does its thing and figures out which one to return as a reference, which we then store in result. So if we look at the types here, result is going to be a reference to a string or a shared reference. It's going to be the shared reference that we return from longest, which could be either X or Y. And then outside of this block, we try to use result. The key insight here is that since string2 is defined inside of this block, string2 will drop at the end of this block because it owns its own data and it can do whatever it wants. So if we return a reference to string2's data into result, which is outside of the block, then string2 drops at the end of this block. Result could potentially be string2's value, which just got dropped. This is what the compiler is warning us about. String2 does not live long enough. String2 dropped here while still borrowed, and it points to line 25, which is the end of the block that we defined it in. In this case, we can take one of two different approaches. We could take string2, and we could define it outside of the block. This will keep string2 around until the end of the program, rather than the end of this block, because the end of the program is the end of the block we've defined string2 in. If for some reason we needed to keep string2 inside of the block, we could also move print line inside of the block as well, because longest and result only needs to live as long as the end of this block, which is when string2 also needs to live until. Both of these solutions work, and depending on whatever your real-world application is doing, you may want to do one or the other. In our case, of course, this whole block is technically unnecessary, so I would get rid of that whole block instead. But moving the string outside of that block means that it can stay alive until we use the result, which is a reference to one of either string1's or string2's data. So to recap it, string1 and string2 are created and they own their data. We pass shared references for string1 and string2's data into the longest function. The longest function chooses one of those two lifetimes, one of those two values to return as a shared reference. So result gets a shared reference to one of these two values. What that means is that both of these values need to live at least until we use result. When string2 resided inside of this block, because Rust will drop values at the end of a block, string2 would have gone out of scope before we used result. That's why moving string2 outside into the surrounding scope so that it can live until the end of the program fixes our lifetimes issue. It's all about how long this owned data is going to live, and that owned data needs to outlive the reference usage. In lifetimes 3, we discover that structs can also hold references as values. Contrary to the previous example with the longest function, where we can often get away with not naming our lifetimes, when a struct is involved, we do always have to name our lifetimes. We can do that through using the same generic syntax that we used for generic types. We use the single tick with the name A. Lifetimes, of course, can have any name that you want to give them, as long as it's lowercase. So we use the named lifetime for author and the named lifetime for title. In this case, our main example is very basic and doesn't really show off any lifetimes. The name and the title are the owners of the values. We create a book which contains shared references to them, and then we print out book.title and book.author, all in the same scope, all in a line. So this is very doable for the Rust compiler. There are no issues here. We don't need to modify anything or do anything fancy for this to work. In general, I would not suggest reaching for lifetimes in structs as a first solution to a problem. I would always try to have structs that own their data. This makes your entire program easier to work with, easier to reason about, and easier to refactor. That said, this is something you can do. And if you plan on doing it, you're going to have to dive into lifetimes a lot deeper. And finally, we get to iterators, which we've seen a couple of times in other exercises, but this is our first time actively working with them. In this case, we're going to have to make this program compile by replacing these question marks. Then we also want to replace the question marks in the actual tests, which are going to be very similar to what we see here already. So we've got a vec here with banana, custard apple, which I don't think I've ever heard of custard apple, so if you have, please let me know. I have actually already asked other people, and they have also not heard of custard apple. So all I'm doing here is taking each of the values and replacing the values that are going to come out of the iterator with the index at which they occur. So bananas first, custard apples second, avocados third, peaches fourth, raspberries fifth, and I don't think there's anything after raspberry, so this is going to be none. So we've got my favorite fruits, which is a vec, and we have to do something to it to get an iterator, because the iterator trait implements the next function, or requires us to implement the next function. So if you have an iterator, or something that implements iterator, you can call next on that struct. When you call next, it will either give you some value, or if you've reached the end of the iterator, it will give you none. So in our case, this is as easy as taking the vec and calling .iter on it, which will give us an iterator. We specify this variable as mutable because .next will pop an item off of the iterator, which is a state change to that iterator. So next needs to be able to mutate the iterator so that it can give us the next item. Every time we call next, it'll give us an option type. If there is a value, it gives us some with the value. If there is no value left, such as when we're at the end, it will give us none. And that's iterators basics. Iterators 2 says that in this exercise, you'll learn some of the unique advantages that iterators can offer. So follow the steps to complete the exercise. In step 1, we need to complete the capitalized first function. If we look at the tests, we can see that capitalized first requires to take a string and return a capitalized first letter for a string. So for our case, we've got this capitalized first function. It takes a string, and we use input.chars. Input.chars gives us an iterator of characters. This iterator is mutable because we're going to call next on it. So we match on that next, which gives us an option. It's either going to be none. If there is nothing in the string, then we return an empty string. If there is a first character, then we get that first character out of the sum. Then we take that first character, we call to uppercase on it, and then I'm converting this to a string right now, but that actually isn't necessary, so I'm going to remove that. We take the uppercased capital letter, and we convert it into a string with the rest of the iterator as a string. So we use format to construct a template string. The template string puts the capital letter first, and then leaves a space for the rest. Taking the iterator and using as str will give us a string slice that we can then place into neatly this template string. This gives us a capitalized letter with all of the rest of the letters attached. Now we've got 2 passing tests and 2 failing tests. So step 2 is apply the capitalized first function to a slice of string slices. Return a vector of strings. So what we can do here is take words, which is a slice of string slices. We can iterate over that slice and map over each of the values. When we map over each of the values, we're getting each of the individual words in this slice, or what we can consider kind of a vec. So we get a word here, which we can pass to capitalized first, the function that we just wrote. This will capitalize each word for us and return a string, which we can then collect. Collect knows which type to collect into because this expression is the last expression in the capitalized words vector function, and we've specified the return type as a vec of strings. Step 3 is apply the capitalized first function again to a slice of string slices, returning a single string. So what we're going to do here is actually copy and paste the code we just wrote into the exact same place in the new function, and it's just going to work, which feels weird. The first time I saw it, it was surprising. The big change here is the behavior of collect. So because we've specified the return value of this function up here to be a vec of strings, collect knows how to collect into a vec of strings. After all, we've given it an iterator of strings. So all it needs to do is create a vec and put them all in the vec. For capitalized word string, the return value is a string. So if we give it a list of strings or an iterator of strings, the behavior it wants to do is to concatenate all of those into a single string. And if we look at the test, that's exactly what's happening. So we've got a vec with hello space world that we capitalize word string on, and it returns hello world with both words capitalized. Whereas capitalized words vec takes hello world and returns us hello and world as separate elements. Collect itself is super powerful, and it can take a while to fully realize how powerful it can be. The behavior is largely driven by what types we tell it to use, either through the return types or something called a turbofish, which we haven't covered. In iterators 3, we have a two-step process to complete. We need to complete the divide function to get the first 4 tests to pass, and then step 2, we need to get the remaining tests to pass by completing the result with list and list of results functions. In this file, we've got a division error enum that we've created, or has been created for us rather. This contains a not divisible variant that itself contains a not divisible error struct. And the other variant for our division error is a divide by 0 error. We've got the divide function that we need to write, as well as the other 2 functions that we need to process. The instructions say calculate a divided by b if a is evenly divisible by b, otherwise return a suitable error. So the divide function takes a and b and returns a result where the success case is an I32, so the success case is the division, or a division error if it can't work. So a is going to be the number on top and b is going to be the number on bottom. Because b is going to be the number on bottom of the division, if it's 0, we can't do it, so we'll return an error. In this case, we use the division error divide by 0 variant. I then do something a little bit awkward because I don't want to pull in any third-party crates here. We've got a divided by b and a modulus b as the first and second element in a tuple that I assign to result. But why am I doing this? A over b is doing integer division. So we've got an I32 for a and an I32 for b. This means that if you divided 12 by something like 7, you would get a value 1. Clearly, 7 doesn't go into 12 evenly, so we have to have some other process for figuring out if b can go into a cleanly. That operator is the modulus. So if we do a mod b, we'll get whatever's left over as a number. In the case of 12 over 7, the remainder would be something like 5. So that means we can check that modulus result, result.1, to see if it's equal to 0. If it is, then a over b worked, and we can return a over b, which is result.0. Otherwise, we need to return a division error, specifically the not divisible variant, with the not divisible error, which we can construct with the dividend and the divisor, which are the top and the bottom, so you don't have to look those up. A in this case is the dividend or the top, and b is the divisor or the bottom. So with that implementation, our divide function is done, and we are passing all 4 tests, or rather, the 4 tests we're supposed to. The next 2 functions are going to be a little bit fun. So we've got result with list and list of results. They both start out with a variable called numbers. This is just a vec of some numbers. And then we get the division results by doing numbers into iter, which is a way to get an iterator, similar to the way that iter gives us an iterator. We then map over those numbers and call divide on every number against 27. We store that result in division results. So far, so good. We have the same exact code in both places. The first thing we need to do is actually replace these unit return values with a result that represents each of the results. So for result with list, it'll be a result with a list inside of it. For a list of results, it will be a vec with a result inside of it. Both of these mean different things. The result with list will be a single result that contains the list of all divisions if they're all successful. The vec of results will return us a vec of all of the individual results that have happened. So if 1 and 2 succeed, but the third one doesn't, and then the fourth one does, we'll get a result of 2 OKs, followed by an error, followed by an OK. Now, the really fancy part of this is that collect understands how to collect both of these exact same pieces of code into both of these result types. Very similarly to the way that we saw the vec versus the string in a previous exercise, collect can determine what the container type is and what to do with the result. Now, semantically, these both have slightly different meanings, and they get you slightly different results. If you want the errors for every potential division, then you want to go with the second option, the list of results. If you only care if they all succeed, you can go with the first option, which will give you an OK if everything succeeded that contains the vec, or it will give you the first division error it encounters. Again, collect is super powerful, And learning how to best take advantage of it and what it can do will take a little bit of time and a little bit more practice and exposure to collect being used in practice. Iterators 4 wants us to perform a factorial, which is a classic whiteboarding problem. You feel like you're in a software engineer interview yet? So we need to complete this function to return the factorial of some number. We then get a list of constraints. Don't use return, try not to use loops, don't use any additional variables. For an extra challenge, don't even use recursion. Now what I'm going to do is I'm going to start off with a range from 0 to the number that we give, because a factorial is that number times that number minus 1 times that number minus 2, and so on and so forth until we hit 0. So we can go from 0 up to that number and then multiply them all together. Interestingly, there's a function that does that. So we can use dot product, and I can go back and make sure that I use the number 1 instead of the number 0, because multiplying by 0 is 0. Even I make mistakes. So we've got a range from 1 to the number, right? And that'll give us, say we pass in the number 3, right? That'll give us 1, 2, and 3. And then by using dot product, what we end up doing is multiplying all of those together. So it's 1 times 2 times 3, which is exactly what we're looking for. Now you could take an approach and go use a reduce or a fold, as it's called in Rust, or you could loop over something and use a mutable variable. Those are all very valid options, but very often there are functions that do exactly what you want without needing to code it manually. And this is one of the really nice pieces of Rust. It has these higher level functions for us. In Iterators 5, Rustlings says, let's define a simple model to track Rustlings' exercise progress. A bit of a meta exercise, if you will. But we're not going to use our actual progress. We're going to use whatever data they give us in this file. Progress is modeled using a hash map. The name of the exercise is the key, and the progress is the value. 2 counting functions were created to count the number of exercises with a given progress. These counting functions use imperative-style for loops. Recreate this counting functionality using iterators. Only 2 iterator methods, count iterator and count collection iterator, need to be modified. So we've got working code here and failing tests. Count iterator has a to-do, which is why our tests are failing, and count collection iterator are the only 2 that need to be modified. These functions mirror the functionality that you see in the function above them. So count for is the for loop version of count iterator, and count collection for is the for loop version of count collection iterator. In count iterator, we get a map. That's a hash map of the string with the progress value, and we get a value to filter by. So what we can do is take the map and iterate over it, filter out all of the values that we want, and then dot count them. And that's it. We filter for the values we want, and we let Rust count it for us. As a slight note, when we destructure things in Rust, we can also destructure shared references. So that's what I'm doing right here. I'm doing that so that the equality works out over here without me needing to do anything. For count collection iterator, we end up with a slice of hash maps. So we've got basically a vec of hash maps here. And ideally, we want to count all the lessons from all of the hash maps that have a specific progress value. So we can take our collection of hash maps and iterate over it. That gives us each individual hash map when we map over it. Then we can call count iterator, the function that we just defined, with our hash map and whatever value we're filtering for. This will give us the count for each of the individual hash maps for this progress value. Since we have an iterator now of all of the progress counts, we can use .sum on the end of our iterator to add them all up. This .sum is very similar to the .product we used in a previous exercise. So we've got functions on iterators for adding things together, multiplying things together, collecting things into containers, and just counting them. Boxing in Rust is a bit of an advanced topic. In this case, we have an enum called list that has a variant called cons and a variant called nil. This is kind of an esoteric way of representing lists. So an empty list will be list nil, and a non-empty list will be a list cons with a value, and we'll talk about box in a second. But the list cons can have another list cons in it, or it can have a list nil. So this is effectively a recursive data structure, because this cons can just cons onto itself forever. We can always have a cons with a number and another cons, a cons with a number and another cons, a cons with a number and another, and it can just go on forever. The problem with this is that Rust needs to know the size of a data structure at compile time, and you can't do that with a recursive data structure. So the solution to that is to add a level of indirection. and we're going to put a box around this second list. A box basically takes the data and stores it in a different place where we don't need to know the exact size of it, which means that when we want to build our list, we can list cons, but we now have to add this additional level of indirection with box new around our new list value. But we can now do this forever. So you may or may not see box come up again sometime soon, depending on what kind of work you're doing. If you're building simple Rust web APIs, you may not see box again. If you're building recursive data structures, you may see box again. Arc1 is an exercise that centers around threading. Now, this is a little bit of a jump up in level of complexity here because we really haven't talked about threading at all, but now we're talking about data structures used for sharing data amongst threads. The arc data structure itself is a fairly understandable concept. You can create an arc, and then every time you clone that arc, there's a reference counter that increments inside of that arc. Whenever those clones get dropped, that reference counter goes down. When that reference counter hits, say, 1, we know that nobody else has the arc, and thus we can drop it if we want to. The reason it's called arc is because this reference counting happens automatically. This is an ARC, automatically reference counted. So we have two places here that we need to do work. We've got to define something for shared numbers, and we have to define something for child numbers. In our main function itself, we've got a numbers variable that is defined as a vec from 0 to 100. We're going to spawn a bunch of threads to do a bunch of work, so we create this shared numbers data structure. This is where we're going to put our arc. We also create a new vec for holding join handles. Join handles are a brand new concept for us, but the concept is that when we spawn a thread, that returns us a join handle struct that we can then wait on in an iterator later to make sure that it's finished. So we loop over some random range from 0 to 8, and then what we'll do here for child numbers is clone a shared numbers. We need to clone the shared numbers because the thread is going to get spawned and moved somewhere else. So whatever data we pass to it, the thread has to take ownership of and basically get up and leave with. That's what this move means. So we're going to take child numbers and we're going to move it into this closure, and it's going to go off and live with the thread. Cloning the arc, which is meant specifically for being passed off to threads like this, means that we're doing a very cheap clone. We're basically just cloning an ID, and we're passing that data through to the thread in a way that it can access. That thread returns a join handle that we push into the join handles vec. Our thread will do some calculations and print out a value, and we will wait on each of the join handles later in this iterator to make sure that all of our threads have finished. If you look at the output on the left, you'll see that it's not guaranteed that the threads will output in any specific order. We haven't really talked about working with threads very much, so don't worry if this is a lot. Basically what we're doing here is we're spawning a bunch of threads on our computer. We're giving it some data via this arc so that it can all access that data. When we clone that arc and we give it to the thread and it runs away with it, arc gets incremented. When it's done, arc gets decremented, and that's how we know when they're done with the arc. Again, concurrency and threading is an extremely large topic, which the Rustlings exercises definitely does not cover in any suitable depth. Similarly to arc, we also have a data structure called RC. So arc is automatically reference counted, but RC is just reference counted. So we're going to have to do some bookkeeping. We've got the RC type being brought into scope and a sun struct being defined that doesn't hold any data. We've got an enum for planets and a variant for every planet. Pluto, unfortunately, no longer around. And each planet holds an RC to the same sun. So the first thing we do in our main function is create a new RC that contains a sun. And we name this variable sun. So rc.strongCount gives us a count of all of the owners of this data structure, or all of the places that have a count for the sun. For each planet, we're cloning that RC and giving it to each planet. So when we clone, this increments the strong count. This is the behavior that's happening automatically when we do arc that we are now handling manually. So we clone the sun using RC clone, which increments the count for sun, and we pass that to Mercury, which lives in this Mercury variable. Of course, the Mercury.details function is fairly trivial. It just prints out hi from whatever planet it is. So we keep doing this over and over. We keep passing the sun as a cloned value into whatever planet and handing out and handing it out and handing it out. The big catch for this exercise is that there are like 9 or 18 like lines of code with 3 lines each that you need to look through just to find out that this is RC new and not RC clone. So we're going to select each of these 3 for Saturn, Uranus, and Neptune. We're going to remove those and we're going to do RC clone, and we're going to clone a reference to the sun. So now what we've got is every planet from close to the sun to far out gets a clone of the sun and increases the strong count, which we then log out by using the strong count to get the count. After we've cloned the sun and given it to everybody, we make sure that the strong count is equal to 9. And then we start dropping them. So normally this drop function is effectively called when variables go out of scope. We talked about this in lifetimes when each of the strings was owned by its own variable and they got dropped at the end of their scope. We can also choose to drop things whenever we want to. We don't have to rely on Rust to decide when that happens. So we can start dropping first Neptune, which decreases the strong count, then Uranus and Saturn, Jupiter and Mars. And if I remember my planets, it's going to be Earth, Venus, and Mercury next. And then we get down to only having 1 reference count because the sun still exists. And that's true. And you can see this in the output. You can see that the reference count starts at 1. It jumps up, and then starts going down, 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 down as we drop. So there's a lot of boilerplate here, but you can see that we've created an RC that contains a sun. We are checking the count each time. Anytime we want to pass ownership of a value through, we want to do an RC clone on the original RC value. And anytime we are done with it, we want to drop the owner of that data so that it releases that count and decrements it. RC is kind of an advanced data structure, so don't worry too much if you don't think immediately of a use case for this. But there are even more data structures in the Rust standard library that you may or may not ever run into. This particular data structure is called COW, or clone on write, or copy on write is another way that you might hear that referred to. Basically, this data structure is meant to provide immutable access to borrowed data, and if you ever need ownership or you ever need to mutate that value, it will clone that, let you mutate the clone, and then give that back to you. So we've got an ABS all function here that includes a couple lifetimes and includes an argument that is a mutable reference to a copy on write data structure that includes a lifetime and contains a slice of I32s. This function also returns the same thing. So what ABS all does is it takes the slice of I32s and iterates over them. If they're negative, then it tries to get the absolute value of the number and set that as the value that's getting returned. And this is where the magic of copy on write happens. If we don't have any negative numbers, then this value never needs to get cloned because we never try to write to it. If we never need ownership and we never need to write to it, this value will not get cloned and we'll get the borrowed version. It's a little confusing that we're doing a negative here instead of just calling v.abs, which is the absolute value function. But remember that we just checked to see if the I32 coming in here was negative. So doing a negative of a negative is a positive. So technically this is absolute value, even though it's not calling the absolute value function. So we're shown 2 examples in main, followed by one that we need to fix. First, we get a slice of 0, 1, 2 in an array, so a 3-element array. We create a cow from that slice, and we run ABS all on the input. Now these numbers are 0, 1, and 2, which are not negative, which means that when we match on the return value, which is a cow, we're going to get the borrowed variant of the cow because we only need to borrow because we never needed to write to it. None of these numbers are negative, so we didn't change anything. In the second example, we get a slice that has a -1 in it. We create the cow data structure from that slice, and we run the ABS all function on that input. This gives us back an owned cow because this -1 turned into a 1, and we had to write to the data structure. So when we had to change this to a 1, do an absolute value of this, and then set it back in the array, the copy on write cloned that array and then gave us back the new clone. So here we create a slice, and instead of passing in a reference to the slice like we have the past 2 times, we pass in the actual vec itself. So the cow owns the data already, which means that when we do ABS all on the input, we're not going to get back borrowed, we're going to get back owned. And no clone occurred because the cow already owns the vec that it has. Without a deeper understanding or more familiarity, more accurately, with the Rust ownership system, it can be hard to think about these things and reason about how this cow is going to behave. So I would encourage you, if you're interested in the data structure, to go read the documentation and play with it a little bit yourself. So while we've already talked about arc, we haven't really gotten into threading. Threads 1 is unfortunately not the first time we've seen threads in these exercises. So here we've got a main function and we've got a handles, which is a empty vec to start with. We spawn a bunch of threads, we sleep in them, and then we print out thread whatever is complete. After that, we create a variable called completed threads that is equal to 0. We iterate over handles, and every time we get one, we increment completed threads. If completed threads is not equal to 10, then we did something wrong. But there's a problem with the program. The join handle that comes back from spawn isn't being used anywhere, but we have handles set up to use it. So if we let handle equal the return value from spawn, which if we look at the type is a join handle, then we can push that handle into the handles vec, and our program will compile and run. We know it worked because we didn't panic, which means that all 10 completed threads completed. The concept of a join handle and waiting on those join handles for the threads to stop is super important. So while this may not have seemed like very much, knowing that the struct join handle exists and it's the thing that we need to sort of wait on for our threads to finish is pretty critical for writing threading code. In threads 2, we want to share this job status amongst all of the threads and let them all update the same variable. We've already got our job status and the jobs completed wrapped in an arc. We've got a handles vec set up just like we did before. And this time the handle is actually being set up properly and being waited on with the iterator. Now with the question marks here, we kind of don't get any useful output from the compiler because it's a syntax error to have them there. So I'm just going to put in unit there for now and remember that we need to do it later. Or rather, I'm not going to put unit in there. I'll put to do in here. So now we can start seeing the compiler output. The first thing we get is cannot assign to data in an arc. And this is at line 24, so it's inside of our thread. And that's a problem because this is the value we want all of our threads to update. But while arc will let us share data, it won't let us share data that we can mutate. We need another structure to be able to do that. The structure we're going to use is a mutex. So I'm going to bring in standard sync mutex, and I'm going to create something that is an arc mutex job status. And now what we can do is take the status shared that got cloned in here for our thread and grab the lock for the mutex, which could fail, so we're going to unwrap it, and we'll get the jobs completed field after we get control of that guard. What this allows us to do is allows each thread to take the lock and make sure that nobody else is updating this data at the same time, make the change it wants to, and then this lock guard will drop, allowing somebody else or one of the other threads to take it and do their own updates. So down in our to-do, we still need to update that to do the same thing. So we'll get status, which is our original arc mutex. We'll grab the lock, we'll unwrap it, and we'll get the jobs completed field. Notice something interesting about all of the outputs. They happen extremely quickly. So while we can end up in a situation where maybe we don't have 10 completed, more often than not we will. So the takeaway from this one is if you need to share data amongst multiple threads that needs to be updated by each thread, one of the ways you can approach that is using a mutex inside of an arc. I actually think the hint for this threads 3 example is pretty critical to read. So let's take a look. An alternate way to handle concurrency between threads is to use an MPSC, a multiple producer, single consumer channel to communicate. With both a sending end and a receiving end, it's possible to send values in one thread and receive them in another. Critically, multiple producers are possible by using clone to create a duplicate of the original sending end. So most of this code doesn't matter for us. Here in send_tx, the function accepts a Q and a TX, which is a sender, something that will send you 32s. What we do with the Q is we clone one for each of these threads that we're about to spawn, but we don't do the same currently for the TX sender. You can see that the compiler is complaining about values being moved into closures and then trying to use them again later, because we have this TX, we're moving it into this closure, and then we're also trying to use it in a separate thread, which should set off alarm bells in your head. So I'm going to create two clones, TX1 and TX2, and then inside each of the threads, I'm going to use TX1 in the first and TX2 in the second. And now we have a multiple producer single consumer sender being used from multiple different threads, sending back to the receiver. You can see that in main, we set up our channel with a sender and a receiver. We set up the queue, and we call that send_tx function that we just called, or that we just modified, with the queue and the sender, which sets up multiple senders to be sending in different threads. We then wait on the receiver, like it's an iterator, and just keep getting stuff from any of the senders whenever they want to send. In this way, we have multiple producers in each of the threads, and a single consumer blocking our main thread so that we can get results that are being sent to us. All right, macros. Macros 1 is actually super easy. It's just a little syntax error. Macro rules is one way of two that we can create macros, but we won't be going over procedural macros. We're only going to cover declarative macros, which is what the macro rules macro is creating. The macro itself doesn't actually matter because our usage of the macro is wrong. As every other time we've used a macro, you have to use it with an exclamation point. That's how you know it's a macro when it's being used. This is true for printline, which we've used a whole bunch of times, as well as format, which we've also used a whole bunch of times. In macros too, we can see that the Rust compiler is having trouble finding my macro in the scope, and that is because macros behave a little bit differently from everything else, and the order you define them in matters because you need to define them before you use them. Macros don't quite use the same resolution mechanics as everything else in Rust. One day we may get, like a macros 2.0, but until that day, we are dealing with a slightly different resolution mechanic. If you define a macro in a module and you try to use it in a parent module or outside of the crate, you're going to need to use macro use to export that macro or make it available at least. So in this case, we've got the macros module and we've got my macro, which is a macro rules macro defined inside of it. When we add macro use, the attribute macro, on top of mod macros, how many times have I said macros now? That exposes the item, my macro, to be used in main. Macros 4 is similarly trivial, but is kind of a foot gun. When you define macros, there needs to be a space between each of your, say, matches, we'll call them for now. So on line 9, all I'm going to do is hit enter and add a new line between the first section and the second section and save that. Rust format is going to add some semicolons for me automatically on line 9 and line 13, and that's it. Just a syntax error. As you can see, working with macros can be a little bit finicky, and it works slightly differently than everything else you know in Rust. This is just one of the reasons why you should prefer writing regular functions before you go reaching for macros. Although macros do have their place and are extremely powerful. If you're familiar with the world of Babel plugins or something like that from the JavaScript ecosystem, you can think of macros as kind of like built-in Babel plugins. Cargo Clippy is a collection of lints that are kind of like in addition to what the Rust compiler considers critical. Now, the Clippy lints have gotten much better over the years, so I highly encourage you to run Clippy on your code. And in this case, Rustlings is running it for us. So in this case, we see approximate value of F32 const pi found. And that's because we've defined our own pi constant. But we don't need to define our own pi constant. We already have a pi constant. So we could use the pi constants from F32 const pi, and then the warning goes away. In this case, we have a mutable variable called res that is equal to 42, and we've got an option that is equal to sum 12. We use a for loop to map over the option, and then add the number inside of the option to 42, and then print out the result. This is not particularly readable, and we have better ways of writing it. So Clippy tells us the for loop over option, which is an option. We've got the name option and the capital O option type. This is more readably written as an if let statement. So let's do if let sum x equals option, and then we leave all the rest of the code the same, and it works. Here's a bunch of more Clippy examples. Let's start with line 19, which is the first one we see here on the left. This let binding has unit value. So let myEmptyVec equals vec.resize. .resize doesn't return the vec, it returns unit. So myEmptyVec is actually of type unit. It's not really useful to have bindings to the type unit. So printing this vec is empty, see, doesn't really do anything for us. So in this case, that isn't even an empty vec. So we would just get rid of it. Or we could specify vec in a different let and do something else. On line 25, Clippy has correctly identified that we're trying to do the classic whiteboarding interview technique of swapping two variables. It literally just gives us a piece of code to write. So I'm going to replace that with exactly what it gave me to write, and then that warning is going to go away. So we can use standard mem swap with the two mutable references there. On line 10, we have some code. So let option, which is an option of unit, equals none. If my option is none, my option dot unwrap. Clippy is smart enough, and the Rust compiler is smart enough to realize that this is always going to be none, and therefore always going to panic. Clippy knows this because we just did my option dot is none, so we can actually just get rid of this entirely, and the unwrap will panic if it's none anyway, and it won't panic if it's not. On line 14, Clippy has identified a possibly missing comma. So we've got -1, -2, -3. Ooh, we did miss a comma. And then -4, -5, -6. So we save that. Everything compiles. Clippy is happy. It's worth running Clippy on your code just to see what pops up. There are a couple uses of the as keyword, one of which is renaming imports, and the other common use case is casting one type of number to another type of number. Now, while casting numbers like this is pretty ergonomic, it is also unsafe. So you need to make sure that you understand the implications of casting one number to another. If you cast a larger number to a smaller number, such as a U32 to a U8, you may lose data because a U8 cannot hold, say, the number 1000. So if you're going to do these coercions, you have to know that what you're doing is okay. If you don't, you can also use try into or try from and things like that to do numeric conversions. In this case, the Rust compiler is telling us that we can't divide an F64 by usize. So this is total over values.length. Now we'll just say that we probably aren't going to have a usize that is bigger than the F64 can hold. So I'll just say values.length as F64, and this calculation will now work because values.length will now be treated as an F64. The from and into traits are other ways of doing conversions, and they're ways of doing conversions not just for numbers like as is used for, but for pretty much anything, any kind of struct. In this case, if you implement from, it's also interesting to note that you also get into automatically. So here we've got a person with a name and an age. We've got some default values for a person, which is John, age 30. And our task is to complete the implementation of from for person. This is a 5-step process that results in a bit of code. So we'll go through it a little bit now that I've pasted the answer in. So we'll go through it a little bit now that I've written the code. Step 1, if the length of the provided string is 0, then return the default of person. So we're implementing from string for person, which requires us to implement this from function for string slices. So step 1, if s.length equals 0, return the default person. Step 2, split the given string on the commas present in it. String slices have a function called split that will return us an iterator. The iterator is going to be useful because we're going to need to pluck off new values. If we scroll down to the tests, we can see that anytime we use person from, it's being used on a string with a name, comma, a number, or some other, more finagly input. So if we split on comma, it.next should be the name. And that's exactly what we need to do for step 3. Extract the first element from the split operation and use it as the name. If the name is empty, then return the default of person. So to do this, we use let else, which is fairly new syntax in the Rust ecosystem. If you type let else and it complains, the Rust compiler that is complains, you might not have a new enough Rust version. So upgrade. But in this case, I do let with a destructure. So let some name equals it.next. If that matches, then we get name out in our regular scope here. So we can do name.isEmpty. If it doesn't match, which means we get a none, then we return person.default from this function. We do the same thing if it's empty. So we take that name that we destructured out and we return person.default if that name is an empty string. Step 5 is do the same thing for the other element, so for the age, and parse it into a usize. If while parsing the age something goes wrong, then return the default of person. Otherwise, return an instantiated person with the results. So in this case, I've chosen to take it.next again, which gives us an option type. That option type will be either some or none. If it's some, we can map over it, at which point I choose to parse the usize, which returns a result. The next step is if there are too many commas, and there's a test with too many commas, which is how I found this out. If we have any more values, that means there were too many commas. So if we have 2 commas, that means we'll have 3 values here, which means that we'll get 1 here, and we should return a default person. Otherwise, this will return none and nothing will happen. We then take age, and it's wrapped in a sum from being it.nexted and wrapped in a result from being parsed. If it's sum okay num, then we can return a person that is instantiated with the name and the age. Otherwise, we return the default. This is a particularly odd implementation of from. Normally, I would see this written as a parser if we're going to take it in as a string, but you can do this and it works. So take that for what you will. The from string exercise is very similar to the from into exercise, but this time we'll be implementing from string, and this time, instead of returning the default, we'll return errors instead. Once we implement from string, we'll be able to use the parse method that we've used to parse out integers previously to parse out a person from a string. The person struct is much the same, with a name and an age that are a capital S string and a usize. This time we have a parse person error enum that includes empty, bad length, no name, and a wrapper for a parseInt error. The logic here is basically the same, but shakes out slightly differently. We implement from stir for person. We use an associated type error for labeling the parse person error, and then we implement the from string function, which takes a string slice and returns a result where the OK value is a person and the error value is the self, which is person, error, which is the parse person error that we defined right here. Firstly, if the length of the provided string is 0, an error should be returned. So if s.length equals 0, we return an error that wraps a parse person error empty. Step 2, we need to split the string on the commas present in it. We do this the same way we did this in the previous example with the split, which gives us an iterator. The iterator again is labeled as mutable because we need it to be mutable to be able to call next. For step 3, only 2 elements should be returned from the split, otherwise return an error. It turns out that putting this in the same place that we had it before doesn't matter. So we'll leave it down there so that we can do it.next after we do the first 2. The only change to this part of the code is that we return an error that is a parse person error bad length instead of returning a default person. Step 4 is to extract the first element from the split and use it as the name, while step 5 is to extract the age. So we use letElse to pull the name out of it.next. It.next returns a sum or option value. If it returns none, then we return a parse person error, no name. Similarly, if the name is actually empty, the same error gets returned, no name. We use letElse again on age. So we use it.next to get the age string. If there is an age string in the iterator, then we continue. If there isn't, we return bad length because there should be a second value here. Then we let the age equal the age string that's parsed into a usize. If there's an error, we map over the error to wrap it in the parse person error parseInt, and we use the question mark so that if there is actually an error here, it gets returned to the top of the function and age gets unwrapped. If we look at the type inlays, we can see that age becomes usize because of this unwrapping. And finally, when we return the person after everything has been evaluated, we need to wrap that person in OK because we're now returning a result from this function and we have to return the success variant of the result type. There are many ways to convert between 2 different values in Rust. We've seen from and into already, as well as the as keyword, but there's also another trait called try from. The main difference between from and try from is that from isn't allowed to fail, whereas try from is allowed to return a result. So in this case, we have a struct color with red, green, and blue fields. We also have an into color error that has a bad length and an int conversion variant. Our task is to implement try from for a tuple of 3 I16s, an array of 3 elements, as well as an arbitrary length slice. First, we'll cover the try from implementation for the tuple of 3 elements for color. We define the associated type error as into color error so that we can use it as self error down here. And the return value, of course, is going to be a color or self. The question marks really help us out here, and the tuple already gives us a guaranteed 3 items. So we can go tuple.index, try into, map error. Try into exists because I16s and U8s are different numbers. Specifically, they have different sizes. So tuple.0 is an I16, but we need to try to turn that into a U8. If it fails, we want to map that error into an into color error int conversion variant. This process is the same for all three fields, and we can use the question mark on all three fields in case there is an error in any one of them to return the error from this function. If there are no errors, then all of these values get unwrapped and used as the field values for red, green, and blue respectively. We have to wrap our color struct in an OK, and we're done. Similarly, in the try from for a 3-element array, the only big change from our previous implementation is that we access array elements with square brackets instead of a dot and then the index. Otherwise, this is the exact same code. And finally, a slice of I16s is almost the exact same code as the array of 3 elements, with the caveat that we check to make sure that the slice length is actually the length we need it to be. If it's not, we return an error with a bad length. If it is, then we do the exact same thing we did for the other two examples. There are some interesting traits in the Rust ecosystem like asref and asmute that allow for cheap reference-to-reference conversions. But what does this actually mean? If we look at the tests, specifically different counts, we can see that s is set to a string slice of café au lait. We can see that if we use the char counter function on the string, it will not equal the byte counter, but this is almost entirely because there's an E with an accent on it in café. If we use just ASCII characters, then the char counter and the byte counter match up. But if we're going to count characters and we're going to count bytes, we have to be able to convert these references into something. In this case, char counter takes an argument, calls asref on it, calls chars, and then counts. Similarly, the byte counter calls asref and then calls asbytes and then calls length. Because we've already used the asref function, the Rust compiler already tells us exactly what we need to do, and that's specify the trait bound for asref in byte counter. However, if we write it exactly like the compiler suggests, we run into another issue, which is that asref requires an argument. In this case, in both cases, we can use asref with the stir type so that whatever argument we pass in here can be treated as a reference to a string. So now we've got 4 passing tests and 1 failing test. The failing test is specifically for squaring a number, and that's because we don't have a function body here. We can take advantage of asref and asmute using the plus to include both as a trait bound like we've done before. This allows us to take a mutable reference to the type that's being passed in and then dereference that through the mutable reference. So we're getting this asmute and set that value that we've dereferenced to equal to the arg as reference to the second power. In this way, we've declared only exactly what we absolutely need for this logic to be able to work. And if we look at the test, mult_box, we can see that the number is a boxed U32, which if we pass into num square, can be treated as a reference to a U32, so we can set that value. And congrats, you made it to the finish line.